machine. We made one in situ soil tester and we used it at 5,500 meters. With all this data, now we are into developing a mining machine which can go to 6,000 meters and mine the minerals available there and pump it back to the surface using a riser system and a very high powered positive displacement pump which can pump at the pressure of around 120 bars actually. So this and we also developed a underwater drill which can go and sit at around 3,000 meters water depth and take a core of 100 meters. This is not actually a silver bullet or it's not a replacement for the drilling ship, but it at least for many applications this can be actually a game changer. Okay. And we also now after doing all these things, we wanted to popularize this underwater technology. So we started something called SAVE competition, Student Autonomous Vehicle Competition. And we encouraged many institutions like IITs, universities and all to participate in this competition. And we used to give them prizes and we used to send them to San Diego and other places for the international competitions. We are happy to see that actually some startups actually started from this and are doing so well actually. It is really proud to see them doing so well in these things. But I'm happy to note that these startups actually, they're just not making ROVs. They are giving value added services to that one. That's what make their product and their technology very unique actually. So now after doing all these things, now we are into developing a manned submersible. My colleague Dr. Ramesh will be able to, and Dr. Radhachalan maybe they'll be presenting details on that one. It suffices to say that here that it will take 3 human beings to 6,000 meters water depth for a time of around 16 hours. In the emergency conditions, it can be extended to 96 hours as well. And it is like a platform, as you know, you don't have control over AUV and the ROV has limited research, limited reach actually. If you combine these two things, we have a manned submersible. We have made considerable progress. God and government willing, I think in 2025 we'll be able to demonstrate it in deep waters. But at least in 2023 we'll be able to demonstrate in shallow waters. And we need to join hands now. We are working in actually in isolation. This doesn't pay actually. I think we should, there is no point in all of us actually competing with one another. We should complement one another actually. So we have to, the synergy is very important. Seeing that Ministry of Earth Sciences, Government of India has launched a deep ocean mission with 6 verticals. The first vertical is on ocean technology, where we all can work together. And coming to the future of this technology, so I can see two aspects which have not been means really taken forward. One is that swarm technology, to use many autonomous underwater vehicles together in actually in coordination. And second is biomimetic vehicles actually. In my view, this is the future of underwater vehicles in the world actually. So with these few words, I request you to excuse me. I have to go back. There is a team led by Norwegian ambassador and our director, our secretary, Dr. Ravichandran, is visiting us actually in the next room they are meeting. I excused myself and came here, so I have to go back. And I hope you'll have a good presentations by the other members and speakers. And at the end of the thing, actually, there will be I believe that there will be a panel discussion in which actually we can check out the future plan of action. Thank you.
So thanks for your time. And there is some question answer from the industry. If they can ask, they can be discussed actually. Maybe we will take forward after the presentation of us with the panel discussions also, then we can have a clarity there, sir. Yeah. Because time is very short. So thank you very much for your time and sparing our valuable thoughts. We'll take forward. Thank you very much.
Thank you.
So we will move forward with our today's presentation and discussions. Anyway, what our director was telling that we will be having a detailed presentation by me as well as Dr. Radhachalam to covering the unmanned vehicle developed at NIOT as well as the manned submersible which is under development. So then any questions which you are looking for, it can be interacted. and we will be ready to answer for all the questions. So we will move forward with the discussions. Next speaker for today's talk is our Mr. Pramod Maurya, who will be talking about the autonomous underwater vehicle. Actually, NIO developed first vehicle Maya way back, and then it has been transferred to the L&T also, the technology. And what are the further technologies which is developed by Instrumentation Division from National Institute of Oceanography, Goa. Mr. Pramod Maurya will be presenting that in detail. So you'll have interaction. With these few words, I welcome Pramod Maurya to give his talk. Thank you very much.
Thank you, Dr. Ramesh. So without wasting much time, I would share my presentation. So can you see it?
Yeah, please. Yes.
Thank you. I would like to talk today on this platform about technologies which we have developed at NIO. And at the end, I will focus mostly on the two most recent technologies which we think can do good for the study of coastal environment and work which can be done underwater in the coastal regions. So we started our work long time ago in 2004 by transforming a remotely operable vehicle which was moving on the surface into a marine robot which would move by itself on the surface. So that was our first project in 2004 when we started at NIO in marine robotics to develop an autonomous surface craft. And we thought that it would be an extended arm of a ship which you can put it out from the ship, throw it in the water, give it a mission, it would move around, and you can move to the next point and deploy another one while they're doing the survey. While coming back, one can collect these surface crafts. So this was the main idea, and also this was starting from the scratch on marine robotics. So we had to learn a lot of algorithms on guidance, control, navigation, mechanical sealing, and all that stuff. So this vehicle was started work in 2004. We built a small one which could be doing like chlorophyll measurement on the surface, and then finally we built this small one which could do for very near coast bathymetry. And this was some of the coast in Goa were covered here. This is Kandolim Beach, 8-kilometer long transects were done very near to the sea, very near to the coastline. So it is like the depth here is approximately 2 to 3 meters, almost touching the surf zone. So this is a challenge that when you have such vehicle and it goes into the surf zone, how would you still be able to maintain its stability when the waves are pretty high? So this work was done recently, and we have been using this vehicle for bathymetric survey, especially in lakes and very coastal area. Right after that, we thought that why don't we go into third dimension, that is diving. We were covering the surface, and we thought that it would be a good idea now to get into underwater environment. And we started by building this vehicle, which was the first time we developed an oceanographic measurement vehicle which can go under the water. We called it Maya. And this vehicle was a torpedo-shaped vehicle with 4 actuators, which are like a rudder fin actuators, and just one thruster. And it was modular in terms of its nose cone, that you can change the payload by changing the nose. So you could put the payload. This is mostly for mid-water column studies, where you could study oxygen levels, chlorophyll levels, CDD, the temperature profiles in the water, and also how the light goes under the water. So this vehicle was extensively used in coastal area, not only in coastal area, but also in estuaries. So we had done 20 to 40 kilometer long run in Mandavi and Zuari estuaries. And this project was quite a successful, and then it was, the technology was transferred to Larsen and Toubro, so that it can be used for further for defense applications or for other oceanographic applications which are requirement of the country. Right after that, there was one more need that many people, when we go on the ship, we have this wired CTD connection, which means that we lower a profiler which is wired, and using a winch, it goes down, collects the water samples. It also collects the water quality parameters, and then we bring it up, analyze it. but this device would always be connected with the ship motion. So we thought that why don't we isolate the device from the motion of the ship? So when the heaving, the pitching and rolling motion of the ship will not affect the data collection by this device. And also because this device is a very small, lightweight device, that it can be used in coastal area by using a very small boat where the winch and all other capabilities are not possible on putting such small boats like fishing trawlers. So you could just throw it into the water and it would based on the mission, it would go down to the depth which is required, collect all the information which the sensors are mounted on it. It could be water column sensors, or it could also be camera-based system because it can also go very close to the seabed. So this technology was awarded also by NRDC Innovation Award in 2010, and we transferred the technology
He's
First is out.
yes, faked out. Just I will check it out, then just a minute. This is the only issue comes into the online platform, so we have to manage.
Yes.
Yeah. Now you are back. Actually, in between you are out of.
So is the slide still visible to you?
No. You please share again. I don't know why it has gone out.
Yeah, I also maybe some internet issue here. Okay. Do you see the screen now?
Not yet.
Not it.
But you are able.
Can you? I don't know. Maybe I'll just disconnect and connect again. Just give me 2 minutes.
Online meetings are many ways it is advantageous. We can connect and do our job, but sometimes this connectivity issue is the very critical. Yes. Your audio, please.
Yeah, sorry for this glitch. I hope I'm starting from where I left. So this was the technology which was awarded in 2010 as an NRDC Innovation Award. And there have been many users, and recently two of these units were also sold to BARC for environmental monitoring in water. Now, the principle of this unit is fairly simple. It remains, when you throw in the water, it remains vertical because the center of gravity and the center of buoyancy are adjusted in such a way. And in the beginning, the buoyancy of the vehicle is more than the weight and the thrust. So that means the vehicle would just float. And as soon as we start the propeller, the thrust force will become more than the buoyancy, vehicle would go down. And then it has an echo sounder to detect the sea bottom. So we can adjust the thruster in such a way that the thrust and the buoyancy can be just equal to each other, and the vehicle would be hovering at that place, either maintaining a certain distance from the sea bottom or maintaining a certain distance from the sea surface. And then you switch off the propeller and the buoyancy becomes greater. The vehicle goes up back on the surface and it transmits its data or whatever information we would require it to transmit. So this is how it works. But there was a but such vehicle cannot be used during the monsoon, and this graph shows that during the monsoon the number of ships which goes into the water are very less. So that required during the Indian monsoon, can we make a system which can still acquire the data and transmit in near real time? And that's when we started a project, which is called Seabed Resident Event Driven Profiler. And this unit is more like a vertical profiler, but it sits at the sea bottom. It has a winch system. It has a communication between the two devices, which is up, which is recording the profiles, and the down unit, which is responsible for releasing this profiler. So we can program it in such a way that any given time of the day or any number of profiles per day or number of profiles per month, it can trigger the upper unit to go up based on its buoyancy, and there is a winch which would be releasing it. This winch is a normal tether which does not communicate over the wire. So the communication between the two units is done through the acoustics. And why that communication is very important, that is because of the data redundancy, that you save all the data in the down unit as well as in the upper unit, because for any case, if the upper unit get lost, the data is not lost. Now, other important thing of this communication is when most of the time this unit is sleeping, and when the seabed unit powers on, at the same time the profiler unit also must power on. So that is how they do the acoustic communication. They wake up over the acoustics, the two devices, and then initiate the profile. So this unit have been deployed multiple times for a long time, and this was off Gujarat and off Goa. Here it was deployed for more than 30 days. It has done 66 profiles, and it shows kind of see how the chlorophyll is not really on the surface, which cannot be captured by the satellite, and it shows okay at the depth you have high chlorophyll. So this kind of data can be very useful for these advisory which are given by MOES for fisheries. We also have another technology which we developed, which we call Integrated Coastal Observation Network. So all of these wave rider buoys, sea level gauges, and all our devices are connected through one network, and the data from all of these devices keeps coming to our web server, through which it can be accessed. Now, there is one example during that Hudud time when it was a cyclone in the East Coast. Many of the units were down, but that is the time when the NIO's website got a maximum hit because one of these weather stations there was still transmitting that data to our server. So the most recent development which we have done, which I'm going to talk a little bit more in detail about, is a coral reef and a surveillance robot. And this robot we started building in 2018. And now it has reached to a kind of TRL level 8, where we have demonstrated all in the real environment. And with little more work, it can actually be seen as a professional device which can be used by the industry. So the main application, what we thought of these are seabed monitoring, which includes all kind of industrial application like pipeline inspection and search and rescue, and other important from the environmental point of view that it can be used for coral reef monitoring. So this has, we worked on mechanical, hydrodynamics, communication system, all that which is required for an underwater vehicle, electronic hardware, software, navigation, guidance and control, which we have learned over all these vehicles, and we have become one of the experts in this for underwater vehicle, electrical system, and of course safety of the vehicle itself. This vehicle is designed in such a way that it can still be, it can transform into a long-term device where it can dock into a docking station, maintain itself, and do the surveys as given time, such that, and it will also have its own charging capabilities. So that's a future thing, but right now the vehicle is able to be used as an autonomous underwater vehicle, which can do image and other scientific data collection of any given survey. So the mechanical is in such a way that we have nose cone again used for most of the scientific payload. It is a flat bottom device wherein we can mount number of sensors which are required at the bottom of it. It also have an indigenous satellite modem which actually uses Inmarsat satellites to give you a position when the vehicle comes up on the surface, and it cannot be connected to the radio frequency modems. So this has all the vehicle payloads which are required. Apart from that, it has capability of carrying side scan sonar. It has capability of carrying cameras and imaging sonars as well. So we normally follow a method whenever we have idea to design, whenever we have a requirement from the industry or from the researchers, we usually start a project, and then we, in the middle of the project or in the beginning of the project itself, we try to invite industries to see that how useful it will be for the industry. And one of these inventor user industry workshop was conducted for this device, wherein we had invited people from different sectors of industry, and many of them are already here in this meeting as well. And we gave a preliminary demonstration of the vehicle at that time on the surface. We discussed what it will be able to do, and we had industry right from the beginning on this. And then we moved it, that was a confined water test, and then we took it to the beach here. This is our Bambolim beach here in Goa. And you see how two people can actually take it and put it on the coast. And the water here is very turbid, so underwater images we cannot show you, but at least we can show you here in the video that how the vehicle is moving on the surface. It was carrying two buoys here on the back as a marker buoys, so that we can see from the far where the device is. So getting it to the main work of it, that coral reef monitoring, and getting it to the real environment, that it should be able to take images and videos of the seabed. And this vehicle was operated here in Grand Islands, where it was acquiring the coral reef images underwater. We did several missions there, lawn movers, straight lines, and many other missions which we planned through this. And this is one of the videos that the vehicle was moving. It was actually connected with a small thread on top, so that we could see a buoy on top from the far where the vehicle is, but that can be disconnected. Now our next plan in September is to take it to the Lakshadweep and do a coral reef monitoring missions right there. Right there. So you see this video shows that the vehicle is quite stable under the water. Can you hear us? Yes, I can see the movement.
Yes, you are audible.
So this is about the specification of Seabed. We have been in touch with the industry now to transfer the technology. Very soon, I think we will have the technology transferred to one of the industries who would be taking this technology, modifying it if required, and used for multiple applications of their need. So this vehicle can, this is a quite modular vehicle which can be connected. You can have any kind of payload. We can design it to a different, altogether different applications too. Now, I would do a little glimpse about technologies of the future, which we are now going to work on. So we call it hybrid AUVs, because autonomous underwater vehicles cannot send a live feed right from the bottom because of the bottleneck on acoustic communication. Whereas the remotely operable vehicles are connected through the tether and they are operated manually by the operator which is on top. Now, what we wanted to do here is make an autonomous vehicle which is also connected to the thread through this umbilica from where the real-time transmission of the images are doing. Whereas there is no bot, there is no human operator which is on top. It is self-driven, and in case if the umbilica get cut, also the vehicle knows where to go and complete the mission and come back on the surface. So what we did for that is we bought some recent already hardware which was existing, and we transformed the software completely such that this whole vehicle can be made as an autonomous underwater vehicle, and we could only give the mission survey from the top and just watch. Not only that, we are planning in this that whenever the vehicle sees something interesting based on some artificial intelligence, it would be able to trigger the user on top, wherein the user can take command and say, okay, give me a high resolution scan of that particular area. So this kind of mission will be very near future technology, which we call hybrid AUVs. Not only that, but hybrid communication system we are building, in which we are combining acoustics, optical communication, as well as the radio communication when the vehicle comes on the top. And this is actually a background for the cooperation among multiple vehicles, wherein we operate a swarm of a vehicle, where many of these vehicles can work together, not in cooperation, not only in terms of increasing the survey area, but also in terms of complementing each other, because every vehicle cannot carry all the sensors. So at NIO, we have expertise available with all of the work which we have done on underwater robot design, automation of marine systems. We are very good with guidance, navigation, control of single and multiple robots. We also do hardware in the loop simulations before actually getting into the real environment. And these are the expertise which you see here. With this, I would like to thank Dr. Ramesh to give me this opportunity to talk about the technologies at NIO. Thank you very much.
Thank you, Pramod. Actually, it is really a wonderful presentation with eye opener, and the future direction by which this autonomous vehicle and the hybrid combination which NIO is now taking forward. Really, it will be is a need right now based on the expertise developed at NIO. Maybe actually I request that the industrial partners who are also participating in this meet maybe keep note of the points which we can discuss at the end of the meeting during the plenary discussions also, because wherever you want some clarifications and the transfer of technology details or anything like that, because we can finish all the technology which is developed by the government organization. So it will give us an idea what are all the technology available in the country to take forward an industrialization. Thank you very much. Thanks, Pramod. So we'll move forward. Thank you.
So I will unshare my.
Thank you. So next talk is mine actually. So hope presentation is visible to all.
Not yet. It's coming.
It is visible.
Yes, thanks for this opportunity to CSIR and MOES for organizing this meet. And I will be talking about the underwater vehicles at NIOT, Ministry of Earth Science. Actually, a glimpse of the activity and the background of it already our director has given. And this presentation will be covering the same points with the pictures and then the vehicles which are of that size and all those things. So I'll be talking about these underwater vehicles at NIOT developed over the period of almost 20 years. So my talk will be on the little bit of introduction and the resources where we are in the Indian Ocean and what is the challenge we have on the deep sea technology and the underwater vehicles developed at NIOT. Some of the technologies are transferred and what can be the indigenization efforts. In my view, I put one list there. Maybe we can discuss on that point on this with a summary. So all of us knows that ocean regulates the climate and it has an enormous portion of the planet's biodiversity, food and material resources. So which serves as a locus for significant of human mankind. So the impacts of world population on the oceans and utilization of the resources are to be understood to live in a sustainable manner. So we need resources which we cannot deny, but how best we can utilize the resources which are available in the oceans is the today's talk of the day and many perspectives actually speaking. So how to improve this knowledge? So most of the systems which we were doing for the last 50 years are the ship-based survey and understanding the resources, understanding the seabed mapping and all. Now the technology advancement and our capability building and capacity is built in the country. So we are able to put the vehicles in underwater, and we are coming out with the results now, the recent 5 to 6 years of timeline. So which is give us a more understanding about the seafloor, which will take us further forward to go for indigenization of this technology, because we are surrounded with huge ocean basins on all the three sides. So we have these different type of resources in a deep sea, which starts from the methane hydrates at around 1,000 meter to 3,000 meter, after the phosphorites, which is around phosphorates are around 400 to 500 meter water depth. Then we go into the manganese nodule, which is almost 6,000 meter, 5,500 meter deep at Central Indian Ocean Basin. And we have a cobalt crust around 3,000 to 4,000 meter water depth. Then we have a polymetallic sulfides. These resources are available in Indian Ocean at different places. So if you see the India and then the ocean which is open up for the Indian Ocean, India is big, and there is no nearby country available to explore these resources, because every country has to travel for a long distance to reach Indian Ocean. That way we are in a very advantageous position to explore these ocean basins, Bay of Bengal, Arabian Sea, Central Indian Ocean, Southern Indian Oceans. Already India have a big stake on the manganese nodule and hydrothermal sulfides under the International Seabed Authority to do the exploration right now. So there is a 75,000 square kilometer area allocated to India. Area going on for the manganese nodule and hydrothermal sulfides also at Central Indian Ridge. So basically this will give us what to look for in the deep sea. And there are many challenges in the deep ocean. All of us are aware of it. One is the pressure, another one is the temperature, and the acoustic is the only medium of communication. It's highly corrosive in seawater. A very dynamic medium, because who are sailed in the ocean, we know about it, how to put a vehicle. So heavy vehicles, then it needs a big type of a launching and recovery systems. That's a big challenge, and we have a very small time window will be available for the seasonally. We have to deploy and retrieve suitable materials and the hydraulics, which is connected to that stable platform with the DP. So these type of many environments related technical challenges are available. And over the period of time, we are overcoming one by one on the design perspective. We are now matured enough to take forward on these technologies, but we need that industries to come along with us, because most of the components which we are looking for right now for the deeper water applications are being imported from abroad. So these discussions will take forward for how much indigenization it is possible or in the coming years to take forward in this underwater technology. So all of us know about the underwater vehicle. One is the unmanned vehicle family, another one is the manned vehicle family. So AUV already talked about by our Maurya, and then subsequently by our Dr. Nandi also will be talking about the AUV. So I'll be mostly covering about the seafloor based vehicles and then the remote vehicles. Manned vehicle will be talked by our friend Dr. Vedachalam after me. So basically, this is a remotely operable submersible which is developed by NIOT. It is a 6,000 meter depth rated vehicle. It is a heavy work class ROV, which needs a lot of subsystems. It's a initial design. We had collaborated with Russia. Then from the design, we had taken forward, and then all the components we imported, and then we integrated. Then the test and the qualifications are done by us, component wise. So it has an ROV which can go up to 6,000 meter at the bottom. It will be connected by a tether of 400 meter cable with the tether management system. These two will be together, and then it will be linked by a 7,000 meter umbilical cable on the top as a storage winch. And this is our ship, Sagar Nidhi. So we can see the size of the components which we are handling. So we need a big ship plus a platform. So we have a heavy launching and recovery system to handle almost 8 tons of weight, which is 3.7 tons of the ROV, and then another 3 tons of the tether management system together. It needs a heavy crane, and the cable has to be handled with the traction winch. So we need a traction winch to take the load of the cable once it is released into the water. Then we have a storage winch of 7,000 meter cable. So this cable is again imported from the Nexans. So we had connected this entire vehicle. We have 2 containers. We used to take containers, consoles, and the power systems in our own ship, Sagar Nidhi. This is the vehicle which has been developed and then demonstrated its capability up to 5,000 meter depth. This is the specification of the vehicle. As our director said, it has gone into the different type of seafloor mineral explorations. Basically, it is of 3.7 tons. It's a heavy work class vehicles. Only 4 or 5 vehicles are available in the world on this class. It has a manipulator arm, 2 robotic arms of the hydraulically connected. And it has a scientific payloads also, temperature, oxygen, conductivity, and we can add any of the payloads. And mainly it is driven by the BLDC thrusters. So there are 2 thrusters for the forward motion and 3 for the going down, because it's a buoyant vehicle. Along with the TMS, it will be taken to 6,000 meter. Then it will be disengaged with the tether. And then we will operate the thrusters and 2 for the lateral motion. So there are 7 thrusters in this vehicle. We are looking forward for the development of indigenization towards these thrusters also. And this is how the power systems are getting driven from the ship-based power, and we are going through the 7,000 meter umbilical cable. There is a variable frequency drive, so we are increasing the normal voltage of 400 volt into 6,000 volt, and then the frequency also from the 50 hertz it will be going to 460 hertz. So with that high frequency and high voltages through the umbilical cable, we will be driving to the tether management system, and then again it will be going into the ROV. There are Subsea converters which will give the direct DC voltage for 300 volt and 24 volt for the thrusters, and as well as for the other lights and powers and other sensors also. So we are an industrial partner to any of these components to choose, and it can be indigenized. It is possible, and you can visit anytime to our institute to see the components which are interfaced in these systems. And this control systems architecture houses where we have 3 PCs where we have a pilot and co-pilot screen and then display for the engineering screen. And it has been communicated with the PXI system. Through that, we have a TMS and ROV. We are using the LabVIEW based National Instrument hardware and the software for the controls and operation purposes, which will be connected through the cameras and lights and sensors. And since it's a long vehicle of 7,000 meters, so we need an optical communication to transmit the controls. So we have 2 slip rings coming into picture. So slip rings are the another rotary joints which is connected to 7,000 meter that deck storage winch. And then as well as in the underwater in tether management system, we have an underwater slip ring. So these 2 slip rings, again, in the global, if you see, there are only 1 firm. We can count only 1 firm, maybe 1 more firm. So which are available, and with the proven technology for this type of rotary joints, which will give that communication to the subsea level to transmit all the data sets. So we have a slip rings and which will be connected through the fibers. So we have now the expertise developed about this concept of how the slip rings can be designed and developed, and as well as the termination assembly for the interface of the splicing of the for the underwater purposes with the fiber optics. And there will be a control console. This console also, again, we have done with the indigenized way, but components are again getting imported for the interfaces and all. So we have a control console for, we will be sitting here and operating the vehicle in the 20 feet containers, which will have the manipulator control separately, and manipulator again, it is getting imported from the International Shipmarine Agency at Canada. And this is how the ROV control systems, just to have 1 small pictures I had put here. And we have to have that wirings and interconnections of all the components in a small pressure case. And we have, because 2 underwater components are there. One is a pressure case driven, so where the 1 atmospheric pressure, all the components can be kept. Another one is a pressure compensated devices where we are using for the power systems and all. So these components we will be using with the inertial navigation system, and it will be interfaced with the PXI. Then the command will be going for the cameras and other control systems and all. So we need partners who can also, you can assemble, and that expertise available. It will also be useful for our type of purposes. And as I said, that LabVIEW is our own software which we control with through the NI, and we have different screens which has been augmented over the period of our experience. How to put the screens, all the components can come and displayed during our operations, and in case of any emergency alarms and all those things. And these are also some of the pictures which are taken out from this ROV at 1,000 meters of first trial at the Krishna Godavari Basin, which we could able to get the glimpses of the chemosynthetic habitats at that such larger depths, first time output. And then we had deployed this vehicle up to 5,289 meter water depth in Central Indian Ocean basins, where we had collected the nodules using the push corer, using a robotic arms with the manipulators, which proves that vehicle capability. We undocked the vehicle and we could able to go to the sea floor and get the mapping. Along with that, we can get the output for the scientific needs, actually speaking. And there are photographs we for the hydrothermal sulfides, which has been used for our initial days. These are all the pillow basalts which taken from the 2,853 meter at Central Indian Ocean Ridge. And this vehicle also used in the AN-32 aircraft search operation at 3,400 meter depth, but unfortunately we are not able to locate that object because of the dimension, and because it's a torch-like vehicle, we have to go near to that, and we saw only the soft seafloor with the organisms. We are not able to detect the target. But this vehicle has been multiple usage for different type of purposes. Basically, this technology is proved and it is available with us. And we are also transmitting the knowledge, which when we are doing the operations itself, it will be transmitted to our main base stations by online video streaming, and we can connect to the optical and the modem, and it can be connected to the base station. From NIOT, people can watch what is happening at the deep sea. Another vehicle subsequently we developed because of the market necessity. 6,000 meter vehicles are very cumbersome. It's a big vehicles. Only few vehicles are available in the world. But when we go for the shallow water vehicle, it will be good. That is what the thought process. So we had developed another shallow water polar vehicle, which is a 500 meter depth rated one, which is a polypropylene with the sympathetic foams. It is again 300 volt DC with the 5 kilowatt hour power. It has again the BLTC thrusters. 4 thrusters are there, 2 for forward, 1 for lateral, and 1 for the vertical motions. This is how this vehicle is developed. There is a frame with the polypropylene sheets, and then we assembled all the components on this vehicle. Again, it is 300 volt DC converted from the ship systems, and it is completely, many of the components are indigenous components with our own design, our own termination assemblies. Only thing that the underwater components like thrusters, cables, and lights and cameras, you have to get imported. One good thing happened on this program is we could able to discuss with the upper industry who are also participating in today's discussion. And we could able to make the earlier imported components of the Nexans for the deep water cables. We could able to indigenize this cable, and we have 2 cables now we procured from APAR. Now they had developed the capability of electro-optic umbilical cables development for the shorter distances. So that is one good outcome of this development of shallow water ROV, and we are using well on those cables, actually speaking. And again, there will be a small console, so it can be used in any fishing trawler type of small boats, and we can put together all the vehicles, and then we can go for the operations. This vehicle we had used for in the Antarctic station, the ice shelf mapping, as well as near lake studies, as well as it has been used for the seaweed mapping at 40 meter water depth in the of Mangalore. We could able to see that the seaweeds distribution there. And for the coral reef also in Andaman, some 5 islands, we could able to monitor very quickly within 4 or 5 days of time. And it's a very stable vehicle which has proved its capability for the operation up to 500 meter depth. And it has been used extensively for some of the classified objects identification at around 70 to 80 meter water depth in our Bay of Bengal. And another systems which we are developing is the integrated mining system. It is for the 6,000 meter depth. It has a lot of subsystems components. This system is handled by Commander Gop Kumar. And it has a deep sea crawler, which has a track belt based vehicle. In front, we have collector devices, and the nodules which are available 6,000 meter will be collected and then crushed and pumped to the middle station, and then there will be a flexible riser to go to the top. We had demonstrated the capability of this vehicle for the locomotion at 6,000 meter water depth at Central Indian Ocean Basin. In the coming years, the collectors will be performed, then the riser has to be done. It has a lot of complex technology. Nowhere in the world the technology has been proved, and India is also one of the forerunner on this technology capability proving into the nodule mining systems. And we have also developed the soil tester, which is for 6,000 meter rated before putting into the crawler at the deep sea floor. This is the nodule field at 6,000 meter. It has proved for 5,462 meter water depth. And this is the in situ soil testers, which can be used for the seafloor strength for the shear strength measurements. And we have developed a deep sea autonomous coring systems with an industrial partner from the US. Only 3 systems are available in the world. It's a deep sea subsea drill, which can go up to 3,000 meter water depth and collect 100 meter of subsea core in the 3 meter sections in a robotic way. So it has a large feet on the bottom, which can be opened up with the hydraulic systems and then sit on the seafloor and drill further for the requirements of the coring. These are all the different subsurface. It is like a ship-based drilling unit putting into the underwater purposes. Only umbilical will be connected on the top. It will be similar to the control systems on the power systems talked about the ROSUP 6000 and the crawler-based machines. So we will be from the top using the camera devices. We will be operating the drill machines, drilling units. It has a big frame, and all the power bottles are kept on the one side and the drill heads on the other side. We will be connecting 3 meter sections to go for the 100 meter coring. These are all some of the underwater pictures which were done at 1070 meter water depth and 2000 meter water depth. So these are all the pipes which are connected. There will be a rotary mechanisms from the top of the drill. We can disconnect 3 meter sections. Then we can take back into the magazines. Then we can connect the another tube. We will drill another section of 3 meter. We can use a wireline tool, pick up the sample alone. Again, you can put back. So all the operations, it is of a depth rating of 3000 meter. We had qualified up to 2920 meter. And then we could able to collect 60 meter of the subsea floor from the Krishna Godavari basin. So these are all some of the samples collected from the core samples, which are of scientific interest, and it can be used for geotechnical purposes. And recently we had augmented ourselves for the autonomous underwater vehicle, 6000 meter underwater vehicle. Directly we procured from Kongsberg Maritime from Norway. This vehicle is a 6000 meter vehicle for the exploration of deep sea minerals, which has a lot of scientific payloads like a multi-beam sonar, synthetic aperture sonar, subbottom profiler, ADCP, and all the what we are looking for. It has a 48 hours of a long endurance. So once you program and put it into the water, we can wait and then have the lines covered. If we can pick back, then we will download all the data sets. It can go up to 2 to 5 knot speed. If we are going only with the multi-beam data sets, we can even go for 72 hours of the endurance. So based on our own program, and we can intervene these systems. This is the vehicle which has a different type of sensors and payloads. It is from the Hugin family of the Kongsberg, and it is having already proved for its capability for 6000 meter in different places. Now we procured one system from the Hugin. It is called as a Ocean Mineral Explorer. We are calling as a OM 6000. It has a velocity log and it has a containerized large. So we have to carry a 30-feet container and then put it on the aft of the ship, and it is of a 2-ton weight. So it has its own hanger with the launching platform. So it will be tilted 45 degree and it will be slided into the water autonomously. It will go into the water, then on the pre-programmed way, it will be doing the job. It will surface back. Then there are mechanisms to pick back the vehicle onto the top. Again, we will pull back the vehicle on the top. So this has performed at Norway, almost 1270 meter water depth. It has performed its operation. Now, right now, this vehicle is at NAOT. We are going for the exploration by this September and November for the 5000 meter water depth for the deep sea exploration. And we had, based on our experience on the ROV technology, we had transferred this technology to L&T Defense and Bharat Electronics with the know-how which is available. And we are closely hand-holding them for any requirements if any users are coming. And it can be a first prototype as an ROV which can be transferred. And we had actually also indigenized the shallow water winch for the 500 meter cable and the terminations which are mastered by us for the 6000 meter. So Apar Industries has given us the cable, and then the Ruby International Ghaziabad has given us a winch. We had given the design for them, and they could able to fabricate with even the connecting for the rotary giant for the slip rings also. So one more expertise developed is because for the deep water, you need these termination assemblies are very critical, and NIOT have such a capability in the country to have the termination, mechanical termination, electrical termination, as well as fiber optic termination put together into the one cable. So for operation up to deep water of 6000 meter. Because earlier we were paying for almost 50-60 lakhs for one termination to the foreign agencies. Now we have this capability. We could able to do the indigenized way with our own people in the institute, actually speaking. This technology also we are willing to transfer whomever we are looking for. And we have two facility, this underwater facility which we wanted to convey. That one is the acoustic test facility tank, where we can put any components for the testing. And we have hyperbaric test facility for 900 bar pressure, 90 megapascals. So we can put all the components and then test it with the live when it fails and when it is succeeding. So all those things can be monitored as hyperbaric. So these facilities also available to the industry to qualify any components if they are investing, and then take it forward with our own vehicles. And these are all the few things which I want to put forth into the industrial partners, that we are desperately in need of the BLDC motor-driven thrusters. For all of us, whether it is for NIO or for the defense purposes, defense labs and NIOT, BLDC motors and the deep sea winches of the larger size, and underwater cables and connectors, we are paying heavily to the industry in the international partners. If any industry come forward and we can facilitate for the testing purposes and all, the rotary giants, pressure compensators, underwater cameras and lights, manipulators, low density buoyancy modules for the flotation of the vehicles, and the termination assemblies, hydraulic cylinders and manifolds, latching mechanism. So few which I could thought of put forth into the industry's mindset. As one is, as such, we can make a vehicle which can be transferred and which can be made. But these small components really makes a vehicle in a better comfort zone to integrated way. Many industries can participate and come out with each components, and it can be integrated in India. It will be a great help to technology domain. So at the end, I would like to say that the middle part of the 4 vehicles already we have developed. Then the autonomous underwater vehicle we had procured from the Kongsberg 6,000 meter one. So right now we are on the both end, that is that integrated underwater mining system for the deep water, which will mine and then pump the nodules to the surface, and the manned submersible Matsya 6000. These two are the deep ocean mission critical programs. Right now we are handling, and manned submersible will be, after me, it will be a delivery of talk by the Dr. Vedachalam in detail. And finally, to sum up the discussions from the strategic perspective, different organizations we can form as an alliances, form as a partnership to jointly invest in emerging industries to overcome local market restrictions, diversify our risks, and gain mutual benefits. So how we can work it out, we can think of all these things. And there are plethora of design and development opportunities available to the private sector in this manufacturing for the underwater systems. You might have seen right now the NIO presentation by Maurya, and now this presentation followed by 2 more presentations by our colleagues. So it will give us that there are different technology, knowledge is available with the scientists and technology organizations. How to translate into industry, we can work it out. So it will give us a self-reliance in the design and construction with indigenous components. Is the aim of this meet to have the capability available within India on the product realizations. In order to fulfill these aspirations as a strong industrial base in ocean technology, now time has come for us to be together and strengthen our filling the gaps in the weakness. So earlier we were all in silos, we can put it together and we can come out with a concrete plan to utilize the infrastructure and manufacturing capability and test facilities available within ourselves. So government is encouraging such type of partnerships. So we are ready to support it. And industry and academia is a collaborative roundtable, provides opportunity, roles of the each of us instead of overlapping each other. And it can be with the concrete measures, with the societal centric approach and strategic need and commercial interest. With this, I would like to close my presentation. Thank you. So this is the underwater technology or the period what we have developed as a capability at the NIOT. Based on these technology knowledge available, now the government has assigned the responsibility to us to go for the development of a human submersible, which is a 3 people's human submersible, where we need a much more industrial partnership in the country. Already we are partnering with the collaboration with the R&D organizations and the industries. But all are depth rated components for 6,000 meter. This is also a 6,000 meter vehicle. So where we need a lot of collaborations and then are even brainstorming discussions on the design. And we are ready to take on board all the discussions. With these few words, I request Dr. N. Vedachalam, who is the project director for the manned submersible, heading this activity. And he's a Subsea expert, so working in the industry for many of the in international areas and France. So I request Dr. Vedachalam to take forward the presentation of manned submersible with the instrumentation and sensors. Thank you.
Thank you very much, sir. Am I audible?
Yes, Dr. Veda.
Okay, sir. Thank you. I will share my presentation. Very good morning to all.
Good morning, sir.
Morning. Hope my screen is visible.
Yes, Veda. Yes. Please.
So thank you very much. So I am, as indicated by Dr. S. Ramesh, head Deep Sea Technologies. I am assigned the topic of instrumentation and sensors for the manned submersible Matsya 6000, which is being indigenously developed by NIOT. The name is Matsya 6000. So as we all know, deep water research submersibles numbers are very less in the country. Actually, this work started. Actually, the work on the deep ocean submersible started in 1964 with the launching of Alvin to search the sunken, debris, etc., various things by USA. The first depth, the depth was something around 4,500 meters, and later various countries joined the subsea race actually, followed by France, Japan, Russia, etc. And the depth and the race went up to 6,000 meter water depth. And during 2010 and over 2020, China joined the list actually with the introduction of Deep Sea Warrior and Jailong and Fendoch. They have touched 10,909 meters water depth, which is in the Mariana Trench. So India has also now joined the race to the bottom, sea bottom, for this manned submersible, using this manned submersible Masia 6000. So as we all know, this manned submersible is yes, submarine, mini submarine, which can carry 3 people down to 6,000 meter water depth. It is an untethered vehicle which will be launched from the ship actually. So you can see the submersible being launched from the mothership using the airframe. So the system comprises of 2 parts, basically ship system, which comprises of airframe and launching systems and other respective controls, and other communication devices such as underwater telephone, positioning devices, surface finders, etc. on the ship deck. And the submersible comprises of multiple subsystems, including personal sphere for human occupancy, human safety and support systems, frame, ballast and trim systems, buoyancy packages, battery power for maneuvering and propulsion, control hardware, communication and navigation devices, imaging system, etc. So initially the work on this manned submersible, we started some 8 years back by NIOT. Initially the plan for the ministry was to procure a manned submersible with technology transfer from outside. Later there were multiple challenges, and before 3 years, the government decided that we can, under the Make in India concept, we can develop our own indigenous submersible. In that, the expertise was pooled and the work was started. So this is the history behind this development. So based on this project is being monitored and being guided by various experts in addition to the in-house team. So based on which the specifications of the manned submersible is something like 6,000 meters water depth, and the human cabin, which we call it as a personal sphere, will be made out of titanium alloy grade 23. It will be of 2.1 meter diameter. The main challenge is making the alloy spherical sphere out of titanium. The accommodation will be by 1 pilot and 2 crew. Number of viewports will be 3, 1 by primary and 2 secondary. The vehicle speed will be 3 knots in the forward, lateral 1 knot and vertical also 1 knot, which will be enabled by 6 kilowatt thrusters. Endurance will be for 12 hours and the emergency period will be for 96 hours. And the life support system inside the human cabin will comprise of oxygen supply system and CO2 scrubber system, and that will be designed for catering 12 hours of operation and 96 hours of stay during emergency. And the overall weight is being targeted for 25 tons. The dimensions you can see, it's 9 meter long, 4 meters breadth and 4.5 meters high. So the payload which is designed, which the submersible can take, is around 200 kg, which is enabled by manipulators. It can take this, payloads in pieces actually, and it can put it in the science basket and it can bring it to the top. The propulsion is powered by battery power source, mainly by lithium polymer batteries. These batteries are special batteries which are special compensated. So for propulsion it is 100 kilowatt hour, and auxiliary is 20 kilowatt hour, and emergency it will be 5 kilowatt hour. Total put together, the energy sources on board will be 125 kilowatt hour. The power and control architecture will be redundant because of the, this is a vehicle, and eventually there are possibilities that it may encounter any collision, etc. Therefore, for damage tolerance, it will be a redundant architecture for power and control. Observation will be done using multiple lights and cameras around the vehicle. Then for enabling intervention in deep water, there will be 2 manipulators. One is 5 function, another is 7 function. Naturally, this submersible is enabled by weight buoyancy changes by taking in seawater and dropping the weights. So we have serious drop weights for 800 kg and emergency drop weight for 400 kg. And in case of emergency loss of buoyancy, we have 600 kg earmarked. Some subsystems will be jettisoned to gain buoyancy during emergency. Communication will be enabled by voice acoustic telephone and data telemetry by acoustic modem. Positioning will be done using acoustic positioning system aided by a vehicle-based Doppler velocity logged inertial navigation system, and it will be, getting input from altimeter, depth sensor, and acoustic positioning. Launching will be done using airframe based launching and recovery system, which we are planning to launch the system from our MOS vessel, NAOT operated MOS vessel, Sagarnidhi. So the design team has done lot of basic design, and it has been reviewed by multiple experts, and we have the Norwegian, the global certification agency called DNV in place, who will validate the design or who will oversee the design, and they will give a clearance for mandatedness. And based on this, various subsystems has been identified, and the general arrangement is being made, and the hydrostatic stability is being confirmed for stability and freeboard, and the hydrodynamic analysis is also done, so that the mission period is met with the available energy capacity, etc. So you can see this. This is a human cabin where 3 people will be sitting inside, and there will be hatch at the top for people to enter. So there will be 3 viewports, primary viewport and secondary viewport. And for catering the life support for the people, there will be sensors inside, and there will be oxygen supply and scrubbing inside. So in front, there will be a manipulator to take in the payloads and keep it in the science basket. So there will be communication systems mounted in the top to communicate with the ship. And there will be guidance and antennas for guidance and navigation system, which will be mounted on top, preventing any shadow zones. And this is called the sail, which will be put on top of this one, so that there will be hatch, and during accidental, or during emergency evacuation of crew at sea, water should not get in, to prevent this one. This is like this, and to enable the vehicle to go up and down without the aid of thrusters. By this one, we have something called a ballast management system, called main ballast system, which can take in water of around 3 tons of water, and make it negatively buoyant and go down. And as it goes down, there will be a set of propellers, forward 4 thrusters and lateral and top, which will enable movement in all 360 degrees of freedom. And as personal sphere cannot be alone. It needs to control will be there, and it should be communicated with the exostructure systems. This will be enabled using high integrity penetrators. This is one thing, and there will be service drop weights around, and there will be a penetrator junction box here. There will be batteries which will be located in the exostructure, as I told you, same polymer batteries. And over and above, there will be pressure compensated enclosures in the inside the exostructure to enable electrical electronics component to be kept inside with appropriate feed throughs, etc. And there will be a system at the top, which is called the emergency marker buoy. In case of emergency, that will be released, and it will have a rope which will help the rescue team to guide the rescue mechanism to the submersible which is stranded down. So as encompassing all these systems, to have a hydrodynamic shape and aesthetic view, there will be foam outside. It is not alone the aesthetic view. The foam will give an buoyancy, which will, if you have fixed buoyancy, which will help which will help to neutralize the vehicle weight, and have a net positive buoyancy up actually. So in front of this one, lights and cameras will be fixed. It will give a view of this one, and you can see various electrical, electronic sensors and instrumentation mounted on the top for navigation and communication purposes. So the concept of operation, I will give a little glance of this one. As I told you, the launching of the submersible takes almost 3 to 4 hours to go down to 5,500 meters water depth, which is the deepest part in the Indian Ocean. As explained by Dr. Ramesh, we have various resources, hydrocarbon as well as mineral resources, spread over the Indian waters or the Indian Ocean, Bay of Bengal, Arabian Sea, etc. And the maximum water depth is 5,500 meters, and therefore we have designed the submersible to go up to 6,000 meters water depth, and accordingly the systems are designed. So now, as I indicated, this is called the main ballast system, and this is called the variable ballast system, and there will be some drop weights which will be fitted on board the vehicle. So this will be launched from the ship, and at that time this main ballast will be empty, and when it is floating, it will give a freeboard of some 1 meter. So for 1 meter as per the statutory requirements and safety. And then when it is ready for the deployment, or when it is ready to dive, so the main ballast tanks will be filled, and it will attain a buoyancy of negative buoyancy, so that negative buoyancy is 300 kg, and it will have a terminal velocity of 30 meters per minute, and it descends down at the required rate actually of 30 meters per minute. And the important thing is that before going, and in between, what happens is that because of the salinity of the water and the compressibility nature of the water, the different parts of the submersible will be subject to different type of compression, and therefore there will be a change in the buoyancy. To counter this buoyancy change, we have drop weights of the various denominations, they are operated by individual actuators. So some certain weights will be dropped at predetermined depth so as to maintain the descent velocity at the desired speed, descent speed. And before touching the seafloor, we have to decelerate and you have to stop to prevent hitting from the seafloor, and therefore we drop certain number of weights at the particular altitude from the seafloor, and we become slowly neutrally buoyant when it is closer to the seafloor. And few hundred meters above the seafloor, we will be carrying out a survey if required based on the mission for a predetermined duration to locate the targets or to have a survey definition, etc. And then what we will do is that we will, this is a variable buoyancy tank, and we will fill the variable buoyancy tank and we will go closer to the seafloor, and it will be near neutrally buoyant so that we will use the thrusters for minimum for going front and back, and we will be using the top thrusters for minimum operation. And then once the mission is completed, the way we went down, in the similar fashion, we will do it in a reverse way so that submersible comes to the top, and when it comes to the 100 meters below the seafloor, so in order to confirm the availability of the ship and the closeness of the ship, the communication will be made to the mothership, and then the main ballast will be evacuated, and then it will surface and it will be taken on board the vessel. So as the title speaks, instrumentation and sensors. For all these things, human beings are sitting inside the perforated enclosures. So sensors or instrumentation are the only means from which the inputs from the various subsystems will be drawn inside the human cabin for making decisions on operation. So sensors are very, very important, and instrumentations are very, very important. As it has been explained, the instrumentation and control requirements fall in multiple categories. It should have high precision. It means low standard error should be there, and it has to be repeatable. Repeatable means random error should be very, very less. The value should be, consistent, and it should have a low bias error. Low bias error is that, for example, if some sensors which is deployed for navigation purposes, if it has a bias error, it will get accumulated over time and it will build up, leading to larger position deviations from the target, which is not acceptable in terms of survey mission or human safety during recovery. And the reliability should be very high, low failure rates, MTBF should be very high, availability should be high. Availability in the sense there should be a less time to repair, and then on-demand reliability for safety critical equipment. As we know, the safety critical equipment like drop weights or the emergency relief systems all will not be operated normally because it will be operated on demand. It will be something like a car brake, which is used in European countries, because in India we use the brake frequently, so it is not the case. In case of European countries, brake will be used sparingly, emergency brakes. So it should be available on demand, and therefore these instruments, whatever we use, whatever it be, whether inside the human cabin for human health monitoring or ambient monitoring or the navigation, positioning or the propulsion, all should have SIL rating so that SIL is connected to human safety. There are various grades of SIL, SIL 1 to 4, depending upon the criticality of the mission and number of people involved and the how long the process is going to take place. SIL is a study subject by itself actually. So as I told you, the instrumentation and control architecture, if you can see. So this is the human cabin. All control systems are located inside. So we have a data acquisition system. We have a pilot PC, co-pilot PC, navigation PC, everything. As you can see, it is axisymmetric. So it is a mirror image. It will be there so that failure possibilities can be reduced and availability can be increased. And all these systems are connected to the exostructure through high integrity penetrators. Penetrators are advanced version of seals and these things. And connection to the exostructure systems, including data acquisition enclosure, batteries all be located in the exostructure. Everything is done using a special arrangement called pressure compensated junction boxes, where it will pave a way for reducing the failures, etc. There will be two main batteries in the port and starboard side, which will be interfaced directly to the junction box and intern to the personal sphere, and it to the power distribution enclosure. Two enclosures will be there, which houses power conversion systems enabling variable speed operation of the propellers. These are the propellers. And we have the data acquisition and imaging enclosure. This is also axisymmetric architecture, will be connected to this one. And we have service drop weights, emergency drop weights, also symmetrically the same. So the thing is that under any circumstances, we comply with the SIL 3 level of architecture, and the moment the safety reliability integrity level falls below SIL, a decision will be taken by the pilot to surface back. without compromising the human safety. So now I have told what are all the instruments which are located inside the human cabin and the exostructure. Now the thing is that there should be a proper network which should integrate all the systems. For example, network, LAN network in our offices. Like that, submersible also has various networks. It comprises of Ethernet, fiber optic backbone, which is integrated. All the systems, for example, this is the processor and this is the processor. All will be connected in ring topology and operate TCP/IP Ethernet protocol. And the medium is single mode fiber optics basically. That why we are going to have a ring topology is that compared to a star topology, which is simple. This is because of the high reliability, because if even when one link breaks, the processor can come into the network through the other way. So considering all these things, we have four enclosures, dry enclosures, and we have four processors in all the four enclosures, and there will be two enclosures redundant here. So all the six processors will be connected in the ring topology in the network architecture. So as I was telling you, this human cabin, instrumentation and control systems are very critical. Basically, it is like a cockpit of an aircraft where you can see pilot PC, co-pilot PC, navigation PC, all these things mounted on all the switches, all the indicators, joysticks for propulsion, navigation PC, control PC, gyroscope, all these things will be mounted inside the very compact space. It is a big challenge because you can see all these things located inside a 2.1 meter diameter enclosure. Not alone this one, we have three components inside this one. First is the comfort level for all the three human beings because they are the important for the mission because it's a manned mission. So all these three people have to be comfortable to a reasonable extent during the normal operation as well as emergency period, that they occupy 30% of the space, and 30% of the space, rest of the space is occupied by instrumentation, and rest of the 30% of the space is nearly occupied by life support system, which comprises of oxygen cylinders, nitrogen, etc. So you can see this is a view. This is not our view. This is the view to show the complexities of how a human cabin should be engineered and populated so as to have the best possible ergonomics as well as ease of operation and comfortness. So you can see the night view when it is lit inside the human cabin. Even though it looks slightly bigger, the photograph is taken in that way. So in that way, we are planning to make the thing for Matsya 6000, taking into aspect of uh, reachability, easily readability. Mainly the thing is that these three people will be here during 96 hours of emergency. You remember, you can understand how the psychology of the people will be there, what will be the energy level. So the switches will be placed in such a way that it will be easy to operate. So you can see this is one side, one hemisphere of the personal cabin. If you see the second hemisphere of the personal cabin, you can see a lot of oxygen cylinders which are mounted in a very compact way, and there will be carbon dioxide scrubber which will scrub the carbon dioxide and keep the oxygen levels at the predetermined level. Then you can see fire extinguishers, emergency breathing apparatus, etc. So these life support systems are made to support 12 hours and 96 hours of emergency, totally 108 hours. And there will be carbon dioxide scrubber. When the carbon dioxide exceeds the predetermined limit, this will start the operation, and they are based upon soda lime chemical actually. So the emergency breathing apparatus is that in case of any fire or smoke inside the personal sphere, complete power will be shut off, and what we have to do is that we have to wear the emergency breathing apparatus, and they should be able to support 4 hours of ascent. So even though the system looks comparatively simpler compared to a normal submarine, defense submarine, etc., which is operated at shallow waters, here the ascent time is 4 hours, and the space is very small, and therefore this poses a technical challenge and realization problems. So as I told you, human cabin internals comprise of oxygen cylinders of 54 numbers, connected in appropriate galleries so as to have the highest level of reliability. CO2 scrubber, there will be two numbers, and instruments will be there for monitoring the pressure, temperature, humidity, toxic gases, fire protection, smoke alarms, etc. will be there. And there will be waste management systems and emergency breathing apparatus, etc. The important thing is that the range of the instruments which are used has to comply with the requirements. So with respect to navigation and positioning systems, we have, you see, this is a Matsya 6000 underwater. So it will have a Subsea GPS which will work on the surface and support the dead reckoning navigation. There will be a depth sensor to see the depth for safe maneuvering. Using this INS DVL, it will determine the position and it will help vehicle navigation. And there will be two acoustic positioning systems. One system will work with relevance to the ship actually. Another system will work with reference to the submersible actually. So both will, through acoustic communication, they will exchange data, and this will help us to achieve the highest level of reliability for the positioning. There will be a mission control system at the top, which will help to connect these devices and see or track the submersible. So this is how the integrated navigation system will look like. So it will have inputs from Subsea GPS, position transponders, two position transponders on the depth, and it will operate the Kalman filter algorithm, and it will finally give the position which will aid the navigation personnel or the crew. So this is how the navigation system will be connected. So the navigation system will be spread across the personal sphere, junction boxes, and the external enclosures, and they will be connected through pressure rated cables, etc. As you can imagine, these pressure rated cables are very, very critical, and they have to be tested to the highest level of, that is, and based on the international norms, they have to be tested at double the pressure to confirm the integrity over time. So another important thing is the underwater communication, basically. So this is done using acoustic telephones. This acoustic telephone we are procuring from abroad, and this is a very niche technology which is able to work up to a depth of 6,000 meters. The statutory requirement is that it needs to operate up to 12 kilometers slant range actually. So it is quite challenging, and only one or two companies are there in the world to supply this one, and that too they are covered under export regulations, and therefore anyone is procuring this with under through diplomatic channels actually. So as you know, the submersible will have lights and cameras all around, because the ultimate aim of the mission is to collect high resolution data on biology, geology, etc. So it will be placed at strategic locations so that everything will be covered around the submersible at a reasonable field of view. So this is how it is interfaced, as I told you for the navigation systems. This lights camera, you can see these are all the lights and cameras, which is integrated through different pressure rated enclosures and brought inside the human cabin, and the recording will be done inside the human cabin. So by and large, you can see the instrumentation and control systems of the manned submersible located in different locations. You can see this is acoustic positioning transponder, up position 1, 2. This is a depth sensor, and this is USBL position tracking system, satellite modem, GPS. All these things will be located this thing in the day. But as of now, as Dr. Ramesh was explaining, everything is being brought, majority is being brought abroad, and now for import, reliance actually. So it is right time for us to embark on to the development of all these systems. Even though NIOT is putting a lot of efforts to develop sensors in-house, but participation of the industry will throw a lot of interest and dynamism and energy towards this realization. As I told you, all these systems will be mounted on the ship actually. This is a submersible A-frame. This mission control system will be kept on board the ship, and there will be a container for life support systems, battery charging, etc. And this will be launched as well. This is a layout which is being planned for launching on board Sagar Nidhi. And as I was telling, the mission control system will be there. There is a guideline called IMC, International Maritime Contractor Association, based on which this mission control system is being designed for. And the more important thing is that during emergency, the submersible, in case if it is stranded to the seafloor because of some problems, if there is an extreme loss of buoyancy, and we have this kind of emergency drop weight, the unique feature of this our system compared to other operating submersible in the world is that this drop weights can be ejected from using the acoustic command from the ship. This is one of the key aspects which is implemented in this Batia 6000. And as I told you, there are increased possibilities that when the manipulator is enabled within an operation or sampling operation or intervention operation, it may get entangled with the seafloor object. And in that case, we are having systems to jettison the manipulator arms alone, and the submersible can come back actually. So this is being achieved with this kind of systems actually. So the thing is that in this kind of jettisoning should be done with the available power supplies. Until the availability of the last power supply, this operation should be able to be done. So all sorts of reliability calculation has been done, all scientific methods has been followed, and the best possible configuration has been given to exercise this jettisoning operation. So finally, if there is a problem of submersible standing to the seafloor and which we are not able to, recover, and if we're not able to, release the weights and come back also, we have a system called, buoy actually, which when ejected by the submersible pilot, it will roll out and come to the top, and it will have beacons, the satellite locating beacons at the top. That is a subsea regulated beacon, which will not work in the subsea, but when it comes to the surface, it will communicate to the ship and the satellite, which will help us to locate the submarine. And there are some systems which will be designed by NIOT, which is something like a messenger mechanism which can be passed through, and it can be locked to the submersible and it can be repaired to the top. It is in the highest level of design actually. So in addition to that, Dr. Ramesh might have mentioned that we have conducted a national workshop to find out the needs of the scientific community in terms of oceanographic and biological and geological perspectives, based on which we have, scientific payloads we have identified. You can see the list of, these are all the oceanographic payloads, and these are all the hydrographic and the geophysical payloads, which is being defined, which is being designed. And these are all the various sampling instruments like push corer, water sampler, etc. And these are the lights and cameras. The engineering system, the system is being designed in such a way that based on the mission, what is a biology related mission or oceanography mission, the sensor suit can be interfaced at with the minimum, disturbing the configuration. So this is what scientific payload is about. So with respect to this one, we have come to a complete design of we have completed the complete design, and the major subsystems of the submersibles are under procurement. Almost 50% are procured, and the rest of the 50% are in progress. The basic thing is that as this is being a mandated and deep water, procurement of the components are a major challenge, because developed countries have reluctance in supporting this one, and many products are developed in-house, and we have taken the help of Indian technological majors like ISRO, DRDO, etc., to handhold NIOT in achieving this national objective, or to put India in the global subsea human map. So with this, I end my presentation, and I thank the meeting organizers for giving me an opportunity, and the listener and the audience to patiently listen to my presentation. Thank you very much.
Thanks, Dr. Vidachalam. Can please unshare presentation.
Yes, sir.
Actually, this is the vehicle which is upcoming right now, because it's a manned mission in underwater. Almost 5-6 vehicles only available for 6,000 meters in the world. So we need a lot of partnership, and then we wanted to disseminate the knowledge which NIOT is doing on this manned submersible program, and there will be more programs will be coming up in the mandated vehicles also in the coming years, based on our success rate of this vehicle. So basically, this vehicle now the design is completed. Even the actually at the positive time, he could not able to see how much components we had already realized also. So we are aiming for the next year end as a target for the completion of all the components procurement and integration and all. 2024 onwards, we will be going for the sea trials for the integrated system. That is what by on that target we are working on it. It is a highly challenging, it's a man-rated vehicle. So we are looking forward for the partnership. So any of the industries who would like to come and discuss with us and partnering with us, we are welcoming for them. So with these few words, thanks to Dr. Vedachalam for giving a nice presentation and overview of the manned submersible. Next topic will be Dr. Nandi from CMERI Durgapur. Actually, CMERI Durgapur is the pioneer institute in developing the underwater vehicle for more than 2 decades, and they have demonstrated capability of the AUV as well as ROV for the underwater purposes. And we are looking forward to the expertise available at CMERI Durgapur. Thanks for his time, and he is willing to share his expertise during this meeting. And they are also done a lot of indigenization for the underwater components, including the VLC clusters. So,
am I audible? Yes, I am sharing my content.
Yeah, please. Yeah, please.
Yeah, can you see my slide?
Yeah, yet to come. We are not able to see.
Okay.
Have you shared through the share window? It is not coming.
Yes, it's showing just connecting. Share content. Also select window screen. Enter screen.
Yeah, it is coming now. It is saying starting to share content. Yeah, maybe you can make it
Now,
to full screen. Yeah, yeah. Can you full screen?
yes.
Yeah, yeah. Now it's coming. Yes,
Okay.
please. Yes, thank you.
So, yeah, very good morning to all of you, and it's my proud privilege to present the activities of in the domain of underwater robotics from CSS CMRI. And I would like to thank Dr. Ramesh and the NIOT team, as well as NIO Dr. Pramod and team, for giving me this opportunity to speak about the expertise of CSS CMERA in the domain of underwater robotics, particularly in the team of E3OW. And I will be mainly presenting that unmanned underwater vehicle and associated systems CMRI has developed, and uh, and the expertise has been acquired in the due course of time. So, probably you are aware that CMRI has was involved in the polymetallic nodule program during 1993 to I think 1998 of Ministry of Earth Science, and after that CMRI has taken the project on development of fast world-class autonomous underwater vehicle in 2003, and subsequently we have taken development of ROV from 40-meter depth to 200-meter depth, as well as 500-meter depth, and we also developed ROV with small manipulation system to handle the payload of capacity maybe 2 to 5 kg, which can be utilized for various possible applications. So CMRI is having the portfolio of remotely operated vehicle technologies, autonomous underwater vehicle technologies, and currently ROV manipulation system, as well as we have indigenously developed the thruster up to TRL level, might be 5 to 6 in that range. So we have integrated robotic system development capabilities under single umbrella through design, kinematics, dynamics of robotic systems, structural and stability analysis from strength and stability aspect, navigation guidance and control, and vision system development and image processing, acoustic RF communication, tracking and data transmission, hardware architecture, algorithm for sensor fusion, and generic software development for system of operation. So this is a typical scenario of working of any autonomous system. So it will be launched from mothership. The vehicle will be operating underwater, and it will have number of payload sensor as well as navigation and navigation and payload sensors. It will have onboard energy system. Am I audible?
Yes, 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 doctor.
Okay.
Clear.
So it will have onboard energy system as well as onboard intelligence. So this intelligence in terms of to take the critical decisions, like when the obstacle, if any obstacles is detected, then it will be able to avoid that obstacle, as well as if there are some critical situation like energy level is very low, in that case it can cut off its mission and it can come up to the surface. So it will have a bi-directional communication link, like acoustic model and USB tracker like thing. So this kind of autonomous underwater vehicle, it should have have a fault tolerant control system, as well as it should have number of emergency safety features has to be incorporated into that kind of vehicle. So this is the broad portfolio, like AUV 150 we have developed, which can operate up to 150-meter depth of operation. So then ROV we have developed from 200-meter and 500-meter depth of operation. Then in the recent past we have also developed autonomous underwater vehicle which can work up to a depth of 500-meter depth of operation. And and very recently we have developed a small ROV, portable ROV with manipulation system, so that it can pick some object from underwater, as well as indigenous thruster that I will be showing in the subsequent slides. So this is the AUV which can operate at a depth of 150 meter. This is a work class AUV, and length is also high, 4.8 meter, diameter 0.5 meter. Weight in air it was 490 kg and buoyancy is 495. The basic objective was to map the seafloor and to collect the oceanographic data like salinity, temperature, and conductivity. The mission duration was for 4 to 6 hours. It was equipped with number of navigational sensors like INS, DVL, and depth sensor, altimeter, and payload sensor in terms of side scan sonar and camera. So it was associated with intelligent controller to perform the autonomous motion like lawnmower trajectory, circular trajectory, or any kind of other trajectory that is envisaged for a particular applications. It was also equipped with hybrid communication system by like acoustic and RF communication. The vehicle was indigenously developed as CSIS CMRI. The design was ours. The control softwares as well as whole system architecture was done by CMRI. But due to lack of availability of the equipment and sensors, that was procured from the outside, starting from thruster, navigational, and payload sensors. But complete development was done indigenously at CSIS CMRI only. So this vehicle was tested at the Chennai coast with active support of NIOT Chennai. So a small video I will be able to see. So it is it is equipped with 5 number of propellers to control the 5 degrees of freedom. So roll pitch here out of these 3 orientational parameters. We have controlled pitch and yaw. Roll was not controlled. It was mechanically balanced. So other 3 parameters like surge, sway, and heave was also controlled. So this was first it was tested at Idukilek coaching, and subsequently it was tested at Chennai coast. And this is the camera view while the vehicle was traveling, uh, you know, uh, based on altimeter based tracking on the lake floor. So this is the sea trial of AV 150 launching and launching operation. Then after mission is over, the vehicle is being retrieved with the help of a frame of Ship Sagarli. So this is the complete GUI for where from we have acquired the information starting from vehicle health, battery status, as well as other critical parameters. This is a small video. So this is this is a small video. I think it is also showing the capability of vehicle which can move based on the altimeter data only, and it can capture the video while it is moving. So this video was captured while it was tested at AEV. It was tested at Idukilek Kochi with the active cooperation of NPOL. So these are the some of the glimpses of the picture that was acquired for during the AV trial, and the mapping of the seafloor was done using the side scan sonar data. So this is the ROV. So I think you have heard a lot of things about ROV, and NIOT has developed ROV up to 6,000 meter depth rating. They have developed polar ROV also, and CMRI has developed ROV 500. So this is glimpses of trial of ROV 500 at Chennai coast. So this is the cable umbilical tether. So ROV it was tested up to a depth of 500 meter. So based on this expertise gain, CMAI has developed, AUV for 500-meter depth of operation with the CSIR funding. So we are very grateful to Ministry of Earth Science, who has helped with funding to develop, to work in this project of AUV and ROV, and we are, based on that expertise, we are able to develop AUV for 500-meter depth and subsequent underwater systems. So this is the AEV 500 that was carried out from the funding from CSIR, and it was tested in 2017 March. So it was associated with the physical parameters of the vehicle is 3.8 meter, diameter is 500 millimeter, weight is 403, and it was having some positive buoyancy in the tune of 5 kg, and material for the structure is aluminium 60676, and the vehicle was tested from the Goa coast, and we have used the ship of NIO because it was a multi-lab project within CSIR lab. Like NIO was associated, Siri Pilani was associated, CSI Chandigarh and CRRI New Delhi. It was they were also associated with this. So we have AUV 500 was developed by CMERI, and we have tested from Port of Goa, and these are the this picture captured by the payload camera, and this is the GUI window where from we will be able to monitor the critical information about the vehicle, and if required we can interrupt the mission. And this is the acoustic positioning data with respect to ship, where the vehicle current position with respect to the ship at current moment. So this is very important. And subsequently we have developed, just a moment. So this is the sea trial. Oh, sorry. This is the video of AV 500. So this is rotated. I'm sorry.
We can move forward actually.
Pardon?
You move forward with the presentation. So
Yeah.
videos we can share it later also if it is distributed.
So this is a small portable ROV with indigenous manipulator. So this indigenously developed underwater linear actuator, and based on that we have developed a tooling manipulator, and that is coupled with a small AUV, small ROV, remotely operated vehicle. So length of the vehicle is 1.2, and width is 0.45 meter and 0.3 meter width and height. Weight in air is 45 kg. The maximum depth is 20 meter, and possible application might be seep inspection and cleaning. So these are the multidisciplinary expertise we have gathered, particularly in the domain of vehicle design, then stress analysis, then hydrodynamic analysis in terms of grid generation, and then control surface design. That how to get the control surface, how to design the control surface for various kind of autonomous underwater vehicle. It might be small range to very high range, then kinematics and dynamics, then sensor calibration, modeling and fusion of sensor data, and of course the robust control, navigation guidance and control, and finally that acquiring the payload data and mapping of the data with respect to that particular scenario. So this is the navigation and guidance scheme. So this is the trajectory planner, and from there we are getting the feedback from different sensor, and based on that, the state feedback, the advanced controller will be taking finding the control input based on the inverse dynamics model, and from there the relevant talks or other information in terms of voltage or current will be sent to the vehicle actuators, and vehicle will move, and the actual parameter will be measured with the help of inertial measurement unit, Doppler velocity log, depth sensor, and altimeter. Then there will be a sensor fusion module. So that will give the best possible estimate of the system state based on the Kalman filter particularly extended Kalman filter algorithm, and that will be also that should be associated with USBL data to get the absolute positioning of the vehicle, and that data will be transmitted to the trajectory planner to get the further control inputs. So further to this area, to the development of autonomous underwater vehicle, remotely operated vehicle to a bigger scale, we are also working in the domain of biomimetic underwater fish fin like actuators. So like fish is having different kind of fins like pectoral fin, caudal fin, pelvic fin, and dorsal fin. So here we have tried to mimic one such kind of fins. So like this is the pectoral fin, and we have carried out the hydrodynamic analysis in terms of blade element model validation with CFD simulation and experimental data. Then load characterization in different operations, multi-fin array caudal fin. So it was related to caudal fin development. Then fish modulates the joint stiffness for maximum energy efficiency. So these and some of the student and faculty, they have carried out PhD in this domain also. We have also strong capability in that domain to take away this work forward. So then, as I said, that we are also we have also developed the indigenous subsea thruster very recently. So thrust capacity is 20 kgf, depth rating is 1500, power input is 1 kilowatt plus minus 20%. So this for this thruster development, the motor is also development indigenously, not by us, but some party based on Mumbai and Gurgaon. So they have developed the motor based on our specification, and other like controller, this propeller, and all the body of the thruster, components of the thruster has been developed at our end only. The test setup also has been developed at our end, and when we have tested the thruster experimentally and based on the CFD data, we have validated it. So then we are also working in the domain of underwater manipulator. As I said, this ROV is associated with a tooling manipulator. The linear actuator has been indigenously developed, and that tooling manipulator with a gripper is associated with the ROV to carry out various jobs, starting from pick some object which has been fallen underwater based on some camera based image processing as well as sonar based localization. So here this manipulator has been developed and it has been tested for hydrodynamic analysis and recursive Lagrangian dynamics algorithm for serial link underwater manipulator with empirical formulations of hydrodynamic forces that has been carried out. And recently we have started working in the domain of homing and docking system, because autonomous underwater vehicle or other kind of unmanned underwater systems is being developed. But what is the problem while we are launching and retrieve? While we are launching, one time it is okay, but when we are launching and battery is being exhausted, we have to retrieve it, we have to charge the vehicle. So there is a tremendous need, extreme need to develop the homing and docking system so that the vehicle can be charged underwater and the data can be transferred underwater domain only, so that with the help of suitable homing and docking system. This is a very challenging task. We have done some primary work in that domain, and we are also going to work under might be deep ocean mission in this domain. So like this is a ROV which is having umbilical cable which can carry out power and signal both. So it is carrying the autonomous underwater vehicle. Then it can the vehicle AUV can come up. It can do the survey, and when the battery level is below the threshold level, then AUV again come to this docking station, and it can do the possible charging as well as data transfer. So it is not required to retrieve the vehicle each and every moment. So it can work might be for a month or uh, might be for a month or year time also if required. So based on the possible applications. So this is a schematic representation of homing and docking system. So possible and future, futuristic activities. As I said, that homing and docking is a very challenging task, and in Indian parlance, it is also required to, develop such kind of system to avoid the retrieval of the vehicle, so that it will not get damaged, as well as to carry out long-term survey and exploration, so that there is a no deficiency of the power, because most of the unmanned underwater systems are till now battery based, and people are now going for the fuel cell based development also, but for that also power is limited. You cannot operate it for indefinite time. So, and current days we are also working on AUVs, which can work for long endurance and long range, for monitoring, exploration, and surveillance in societal parlance, as well as for defense parlance. So then, for that kind of thing, that navigation guidance and control will be a big challenge, particularly when the vehicle is working within the domain of acoustic range. The communication might be easier, but when we are talking about long endurance vehicle, the communication is not there, particularly when it is working underwater. In that case, the formulating or planning a perfect communication framework when the vehicle will be working underwater is a real challenge, and we are working in that domain. So multi-vehicle, portable and stealth class AUVs cooperation, like multi-region system for various applications like wide area search, survey, and surveillance, and hybrid underwater vehicle like AUV, which can work in AUV and ROV mode depending on type of application required. Homing and docking system for UUVs and AUVs, then miniaturized biomimetic underwater vehicles, then UUV manipulation and intervention system for seafall cleaning and inspection, then autonomous and intelligent surface caps, then vehicle with variable buoyancy engine, and slow moving autonomous underwater vehicle for surveillance and monitoring. And of course, the need is development of indigenous components, starting from the propellers, sensors, and communication system. So we have a strong collaboration with NIOT Chennai, and we are hoping to work under the deep sea mission to work to carry forward our work further. And we have also association with NIO Goa, so they are also hopefully we will be working together in the domain of AUV for higher depth rated operations, like maybe 4,000 meter or beyond. So I like to thank Director C. Mira, Ministry of Arts Science, Ministry of Science and Technology, NIOT Chennai, IIT Kharagpur, NPL Cochin, as well as NIO Goa, uh, for carrying out this kind of activities successfully. I also thank all the industry partners who are present here. Somehow we are also looking for to work together, particularly the development which has been taken place in terms of technology transfer, or particularly the current development also, like thruster, what we have developed, how we can carry forward it to further domain or further level, further TRL level. So thank you so much. Thank you once again to NIOT and NIO for giving me the chance to speak in this forum of iConnect, to collaborate research with industry. Thank you so much.
Thank you, Dr. Nandi. It was a nice presentation with the components which were moving forward for the indigenization, really some of the eye openers. So, which is a definite need for us in the underwater domain. Thank you very much for sparing the details. Please unshare the presentation. We have a last presentation for this presentation talk. After that, we have a plenary discussion with the industry. That now we are overshooting into the time. So next will be actually our Commodore Srinivas. He has a wide experience in Indian Navy, with the background with the Indian Navy, so he knows the technology requirement for the underwater purposes. So that need he himself right now is leading the team of people in the last run to grow at Powai. So with his experience, he can put forth the view of the industrial side, and then the futuristic, what is the dimension by which India is going towards the technology development for these underwater purposes. So we requested him to make his viewpoints in a short brief of 10 minutes. So it will be another perspective of viewing the things on the underwater technology development. So far the presentation were made from the government systems which were already demonstrated the capability. So we can, I request with this Commodore Srinivas to present his viewpoints on the industrial perspective of the underwater vehicles. Thank you very much for your presence.
Can I hear you?
Yes, sir, you are audible. So maybe
Yeah, audible. I'll just share my presentation.
Yes, sir. Maybe I request our industrial people actually, because there will be some slight delay is there in the overall. So we will try to match it up. So my presentation will take on the plenary talk. Yes, sir, it is visible and maybe it can be in the full screen.
Yeah. Good afternoon. Is it in full screen now?
Not yet, sir. Actually, it is in the actual screen, but
Some delay is there.
okay, it has come. Thank you. Yes.
Yeah. Good afternoon, ladies and gentlemen. I would like to thank the Ministry of Earth Science, CSIR, and the NIOT for giving the industry an opportunity to present its perspective during this important iConnect event. I would like to thank Dr. Tiwari, Dr. Ramdas, the distinguished members of scientific community of the various labs, and the eminent industry partners who are present today. A little background, which has already been covered. Assessment of technologies, again covered. Challenges are the ones which I would like to bring out, and the various areas of work which has already been covered, but the industry perspective on this and the way ahead, please. As we see on this slide, in 1987,
Yes, sir, it is coming. Yes. Before this slide. Maybe one slide you have to reverse.
yeah, in 1987, India.
Now we are seeing the slides on assessment. Yeah, right now, okay, sir. Background. It is on the background slide. Yes.
India received the status of a pioneer investor and was allotted the exclusive area in Central Indian Ocean Basin by the UN. And thereafter, in March 2002, we entered into a contract with the International Seabed Authority for the exploration. And thereafter, the contract has been extended by another 5 years in 2017. Now, where are we? Almost 35 years. What are the technologies that have been required to be addressed by us? The high pressure systems has been brought out, the remote operation of various unmanned, manned, tethered systems, the complex metallurgies involved, the material requirements, the handling of this technology for these various requirements, which are dual use and therefore denied by various countries who have it. As we have seen in the earlier slides, only 5 countries have put their men to these great depths, and when we do it, we'll be the 6th. The limited countries which have done it, it's been supported by the government, and the industry there has matured and caters only for that limited requirement. So therefore, it's not shared openly, or they are not willing to share the technology with our countries. So whatever anybody else is trying is in a very nascent stage, and the handful of suppliers who are there, who have been working at greater depths beyond 1,000, 2,000 meters, they do not want to share these technologies. In the last around 10 years, L&T has extensively interacted with various foreign OEMs on various projects for NIoT and other underwater purposes for the country. As we know, as we just brought out in the earlier few sentences, these items are not in serial production. They need to be produced on order or as existent requirement exists. So because of these factors, you cannot get an item ready-made even in the commercial market outside. So if this needs to be indigenized, well, what are the requirements? One, it is the scientific requirement for the various research activities. And secondly, it is the commercial exploitation of this technology for various applications. What, therefore, the problems we have been facing is that, as has been brought out, we have been operating from surface to 6,000 meters. It's very, very technology intensive. It requires a lot of a wide range of equipment, from the materials to the control systems and the various sensors, the communication, etc. It covers a wide band of all technologies as equivalent to the space, if we want to take an analogy. And the deep sea technology is not that much explored compared to the space technology. Therefore, the dependency on the import content is very high at this stage because of the limited availability of raw materials and components and the test facility. And if the industry has to invest, as I brought out earlier, with this scientific applications, the numbers are very less, and only when it becomes commercial, then the volumes could be justifiable by the industry to invest in the R&D and the overall indigenization program. And it's very, very expensive. Like recently, we had carried out welding of 80 mm thick titanium plates for developing capability within us and thereby the country. So it's a very, very expensive and intensive field. Now, what are the areas of work which again has been brought out by in detail by various other earlier presenters? I'm just summarizing few of the facts here. Fabrication and manufacturing, high pressure systems and equipment, the cables, connectors, harness, instrumentation and controls, integration of subsystems and systems, test facilities, payloads, and certification and acceptance. So now, if the industry has to take part in various activities, so what could that be? So we need to define if it's for the scientific applications or for commercial applications. Now it's in the region for the control of the platforms per se, the various platforms. As was again brought out in glimpse of in certain presentations, it's the vessel per se, that is a deep vessel AUV or UUV or the manned vessel. Then there is a launching mechanism, which is a different technology and different aspect. And third is the mother platform, mothership. So it's a requirement of three sections. So the customer would need help in all the three. Customer or the government would need help in all these three segments. So the first of all, there needs to be a integrator at the subsystem system level. There need to be somebody to develop the components, as again has brought out in various presentations. And there needs to be a focused time frame and funding for achieving these developments. With the onset of the Atmanirbharta campaign by the government and a lot of emphasis and the trust which has been given by the government in the last couple of years, we need to really expand and have some strategy in place if we have to make a quick progress in the next couple of years in this deep ocean mission. I bring out few policy-related issues. The standard procurement policy and practices cannot be followed as we follow in the government, because as we already brought out, there are a lot of difficulties in the technology. It has to be developed. So certain projects have to be, or the deep ocean mission has to be declared as a strategic project for a period of at least 5 to 10 years. Second, you need to identify strategic partners both for the integration in the various areas as well as for the development of various components. The MOD, as you may be aware, has followed this model for the nuclear submarine program, which is available in the to a certain extent in the open source also, and the DCPP model, which is followed by DRDO, and thereafter the vendor is identified as a developed vendor. You do not tender out again and again. These are not technologies which are commercially available in the market. So we need to promote and support that vendor, and that vendor is married to the program along with the lab to give the country what it requires. So at this stage of the program, the development of the various equipment, the components, the integration, and the realization of the objective should be on the cost plus basis for this period of 5 to 10 years. Then when the technology is developed and the industry is mature enough, then the cost becomes more realizable and supportable. And because it's already developed, it will be realistic as in sync with any commercial product. So to reach this stage, we need to develop the technologies because they are not COTS, place developmental orders on the Indian suppliers. We need to identify the critical subsea components as we are already doing for the various components as required. Then create the testing infrastructure, which again we are trying to develop already. NIOT has taken considerable steps in this process, and only by doing this we would achieve a critical mass in the meeting of our objective towards Atmanirbharta in the deep ocean projects. That's all from my side. Thank you very much.
Thank you very much, sir, actually, for your the lucid way of putting clear what you want up to the level decisions. Maybe if maybe we will request you that to share these points, and then as an outcome of this discussion, we will also share with the CSIR. Then we can take forward. And thank you very much for your time and sharing and your experience and where we can concentrate. Thank you very much, sir. We will move forward for the panel discussion. We have Dr. Vijay Kumar, advisor from Ministry of Earth Sciences. Actually, he is a well-wisher, and he is actually the driver for all our activity of the ocean technology in the government-funded programs from Ministry of Earth Sciences. He is the driving person from the ministry for all the activities, and he is also the interface for the policy from the government side, actually. And he is when I approached him for this panel discussion, he readily agreed for that. Thank you very much, sir, for your presence, because you know that what is the government is looking for and we are doing right now, so it can be connected well, and we can have this panel discussion with our industrial partners. And Dr. Vijay Kumar, actually, he's the person who finally completed the relay race for the deep ocean mission and got the approval of the cabinet note. And right now we are only working on the deep ocean mission programs, which is the pioneer program for the country and for the Ministry of Earth Sciences. With these few words, I request Dr. Vijay Kumar to take forward this discussion. We have almost 8 industries participating in this discussion, from ECIL and PMG submarine projects and Bharat Electronics, System Engineering, Sea Conway, and VMX connectors, APAR Industries, Planis Technology, IROV, like that. All the industries are available who knows about the underwater. I will read one by one the names. So before taking forward on the discussion, I request Dr. Vijay Kumar to take forward this panel discussion on the topic of underwater vehicles, capability, and the technology demand. Thank you very much for your time, sir. Please.
Thank you, Dr. Ramesh.
Yes, sir.
And good afternoon to everybody. So I am listening to all the presentations from the morning, and it was, I can say, very good presentations made by NIO, then 2 presentations by NIOT, then by CMRE, and then the last by LNT. So as such, the capabilities which are available with these, you can say, major agencies dealing with the ocean technology, you are aware like what are the technologies available and what are their future plan in the coming years. So as Dr. Ramdas has also spoken, then Dr. Ramesh has also spoken, and some of the presenters have also spoken. Government of India has launched a deep ocean mission, and one of the component under that is related to ocean technology, and this component is basically led by NIOT, and it has 2 major components. One is development of manned submersible, so which the details has been presented by Dr. Vedachalam, and the other component is development of mining technology. So for that also some reference has been made. And related to this mining technology, this is, you can say, part of the contract which India has signed with the International Seabed Authority. So this contract was signed in 2002, and it was extended 2 times now, in 2017, and then recently it is again extended for 5 years. And as such, International Seabed Authority is also in the process of developing the exploitation code. So as such, because the exploitation code is not there, so they are as such extending the contract for exploration for all the countries. And over the years, we have done very good work related to the whatever is to be done under the contract. And I acknowledge all the participants and all the, you can say, issues, including NIO, then IMMT, then in the beginning CMRI also, who are involved in this contract with International Seabed Authority. Under this deep ocean mission, we have another 5 components, but that is not directly related to say ocean technology. So we have, I think, very limited time, so I will not speak much about these things. So you have already listened. So we have to now basically discuss, like, the capability of the different this thing, and mostly there may be some interaction or between all the institutes. But how we can further increase this interaction in the future and along with the industry, because most of the development which is being done at the institute level, some of the technology has been transferred to the industry, but not all the technology, and then we need also help from the industry to, you can say, for this technology development. So I would like to listen from the other industry people who are attending this event, like what they think about how we can increase the interaction and what is their capability and how they can help, you can say, Ministry of Earth Sciences and IoT and NIO in taking further the technology. So Dr. Ramesh, with this I will close, but I think you have the list of all the industry
Yes, sir.
who are participating, so you can
Yes, sir. I will
request
just,
them to, or you can say invite them to speak. But you
yes.
please take care of the time. How much time? According to that, you please give them the time. And if any specific question or something is there from the presenter, that also they can ask. But I don't know whether they have that much time. But they can raise the issue. If it is not answerable at this time, maybe they can interact more through email later.
Yes.
Thank you.
Yes, sir. Thanks for your time. Actually, as you said that we are now overshooting into the half. So we will maybe another half an hour. We will complete this panel discussion. So we will close this meeting maximum. So now all the industries also might have listened to our developmental capability and infrastructure available, and what is the team, which team is working on what type of technology. And as Dr. Vijay Kumar said, that you can also have a direct interaction. You can come to us and we can discuss and we can take forward any clarifications. And we would like to listen your view. I'll start with General Manager Mr. Santosh from Defense Corporation Software from ECIL. So we would like to hear his views. And we have 8 industries, so we will have some 2 to 3 minutes of time for each. We will listen and we will keep note of the points. So I request Commander Santosh to start the proceedings. Thank you.
Yeah, good afternoon, sirs, and the distinguished panel. I would not like to waste my time thanking each member here. So I think I will straight away get to the point.
Thank you, sir.
Actually, ECIL has been involved with NSTL for development of unmanned underwater vehicles for the defense applications. So what I could make out from the presentation today and with Mr. Vijay Kumar from Ministry of Earth Sciences is that a lot of technologies that we have developed also has applications in the the common commercial area, which we are looking at for sea exploration or sea mapping and these kind of requirements. So I'd just like to highlight that ECIL, in fact, has indigenously developed the mission computer system, which basically is used in underwater vehicles. Then we also have the complete electrical systems, that is the power management system, recovery junction box, mission timer, the actuator, amplifier, potentiometers. I mean, the whole lot of things actually which will go into all these systems. Although we have done it for defense application, as I brought out earlier, but these can be used in your AUVs, which are or ROVs, which you are looking at. Let it be for deep sea vehicles or for the vehicles which are going up to 500-meter depths and things like that. In addition to that, we have also got into mechanical system design with the help of NSTL for the exostructure, payload holding frame, rudders, and we have also identified suitable sub-vendors who can also execute these particular mechanical systems. In addition to that, the power management system is another area where we can look at it, because as we brought out, either it is tethered or independent underwater vehicle, power management on board the underwater vehicle is a major issue because you're going to have battery with limited life. So, so we have an, indigenously developed a power management system. In fact, even we are doing this power management system for tanks, for future tanks with the CVRD Audi, where we are developing these systems where we have efficient power management system within the existing resources that are available. In addition to that, we also have the recovery systems like smoke marker, flasher, noise maker, dump mechanism, etc., which we have actually developed along with NSTL and other, private industry partners. And of course, what I would like to highlight here is ECIL, most of you may be aware, comes under the Department of Atomic Energy. And we are making complex systems for all our nuclear power plants. All the nuclear power plants control systems are being developed and manufactured by ECIL. So towards this, in duly considering the cybersecurity related issues, ECIL recently launched our own PLCs and SCADA systems. So definitely for all the control systems which are going into unmanned vehicles, they are going to use the PLCs and the SCADA based systems. Let it be for navigation purpose or for weapon purpose or even for the recovery purpose and these kind of things. So we have solutions for these things, and we have indigenous PLC and SCADA systems, which in the long run will, having indigenous technology here will always help from, external interferences or cyber from the point of view of cyber security and things like that. We have also put in place communication systems, with acoustic modem, UHF modem, fiber optic modem, and things like that in the kind of underwater vehicles that we have developed. So here, and also in addition to the AUVs, ECL is working with DRDL for many Akash missiles, BrahMos missile projects. So we have got good team for development of software for C4I systems, which you spoke about in your presentation: navigation control systems, collision avoidance systems, propulsion systems, and things like that. So I think what is required as a holistic way, if I want to put it, that I think within the country, bits and pieces of expertise is available. And as Commodore Srinivas brought out, I think we have to bring in the critical mass in bringing all these industries together with whatever already the expertise available. And also, like ECIL or L&T or any other industry is also in the field of business. So, okay, we are ready to invest certain amount of money. We have our own mechanisms of doing internal R&D based on which whatever systems which I mentioned have already been developed. But in case there is some kind of a central funding to this, and with whatever expertise that is available with us, I think definitely we can join hands with NIO and the Ministry of Earth Sciences to develop all these subsystems. And we have capability of doing the integration at subsystem level and the system level. So I think with these expertise, I think we should be able to meet the requirement what Ministry of Earth Sciences is looking at under the Atmanirbhar Bharat of having deep sea mission vehicles and other things. So with this, I think I will conclude. So these are the capabilities that are already there, and in fact, we are already now looking at signing a TOT for the CBOT with NIO, and with whatever presentations which we have given, which has been given today. And I think we would like to partner with NIO for developing all these systems and subsystems and putting one vehicle for this nation. Thank you very much, sir.
Thanks, sir. Thanks for your time, and really very clearly you brought out the already expertise available with ECIL. Really, we will also look forward to interact, and we'll come out with the plan for that, sir, actually. So we will we'll take on next, actually, Commodore Srinivas. Already he has given his perspective. And we have Venkatesh Arasu from L&T. So Commodore Srinivas, you want to speak, or I can?
I will speak towards the end. Arasu can speak now. Yeah.
I request Venkatesh Arasu to give his view from L&T, because they have taken the ROV, AUV, as well as both the technology. They have good expertise on this underwater vehicle, so they know where we are lacking in the country on the industrialization.
Thank you, Dr. Ramesh. Good afternoon, everybody. I'll keep my points short and succinct. As an industry partner, L&T has positioned the various technologies that have been illustrated in today's interaction. We have achieved varying degrees of success. In order to improve the marketability of these technologies in the open market, the indigenous content needs to be targeting more than 50% right at the design and acquisition stage when these programs are in their infancy with the development organizations. Indigenization efforts need to be targeted towards sensors and equipment. Currently, our estimate is that the mechanical systems for an AUV or an ROV account no more than 10 to 15% of the manufacturing cost. Of the balance, almost all components are imported. Though we may have indigenized the vehicle controller and power distribution, in our experience, they are manufactured at a fraction of the cost when compared to the price of sensors such as multi-beam echo sounders, sub-bottom profilers, side scan sonars, acoustic modems, and other payload sensors. That is where the main bulk of the cost lies, cost of these vehicles lie. There is a need to indigenize underwater thrusters, high capacity batteries, and other equipment as already highlighted by our esteemed colleagues in this forum. We are excited by some of the developments put forth by NIO, CMARI, especially in this regard, and look forward to seeing these equipment in the field. However, we feel there is a long way to go before our equipment, and when I say our equipment, I mean in the general context of Indian equipment, is truly indigenous to a degree where it is commercially marketable in the world market. That is all I have to add right now, sir. Thank you for your time.
Thank you, Venkatarasu. Actually, so we will move on, and we have Nalayan, Deputy General Manager, Unmanned Systems Group from the Bharat Electronics. So I request Mr. Nalayan to take his views on this.
Good afternoon, everybody, and thank you for giving this opportunity. So we are closely working with the National Institute of Ocean Technology for transfer of technology for the remotely operated underwater vehicle, which is actively under progress, and we are taking support time to time from NIOT and doing it. And so some of the challenges we face, I just tell shortly. So the time to make is always limited, but actually it is always overshooting because of the volume what we required for making. The volume requirement for the underwater components are less actually for us. But the most of the components what are available in India is less, and we depend mostly on foreign OEMs. So foreign OEMs also there is some volume requirement, and when we buy one or two numbers, so the challenges in procurement also is there. And apart from that, the future business opportunity at this point of time, there is no certainty in the numbers. So we cannot tell that what will be the future requirement. These are the challenges what we see. But however, we are seeing that there is a growth in a lot of products presented by NIOT. The different presentations were telling NAO is also coming with some product, and CMERA, we are having a different component level manufacturing which is also happening, like manipulator, thruster, and that biofin manufacturing is also there, which are all very informative and very useful. And us in Bharat Electronics, what we specialize here is for unmanned systems specifically. So we look into the algorithms and the MI and AI and ML, machine learning, where we have units present in Bharat Electronics Central Research Laboratory and PDIC, Product Development and Innovation Group, where they work closely with us to develop algorithms and the products for us. These products are only design level only, but however, like earlier L&T and other people also told that we depend most of the component from foreign only, because there is no ready components available like sonar, then DVL, depth sensors, acoustic communication modems, all those things. So these are the challenges what we have. Bell NSTL, and they are also working with the defense customer also. They have made some sonars which is a form factor which is not suitable for small vehicles, but however for bigger vehicle they are doing. And our PDAC also is helping us to what you can tell develop smaller sonars, and also there is also DVL getting developed in Bell. And our Central Research Laboratory is closely working with Ministry of Defense. They are making autonomous softwares for autonomous boat, and they are very well versed with different types of means radar processing, sonar processing, all these things. They are also working with 2D map or 3D maps of depth processing and all. So they are almost involved past 6 months, and they are going to next level in autonomous creation, autonomous algorithm creation and all. These are the things we are working on. And as unmanned system underwater vehicle, we are in a preliminary starting stage only. However, so we seek support from NIOT, NIO, and CMERA to take us forward for our future business development. Thank you.
Just a minute. Yes, we will move forward. Actually, thanks, Nalayan, that your inputs are well taken. And next, I request Sri Naga Rakesh, CEO from Sea Convoy Systems Engineering from Chennai. So I request Sri Naga Rakesh. So I request, you're not audible. Mute. Naga.
Avanish,
Your
you
audio
are
is-
mute. We cannot hear you.
Can you speak now?
Yeah, hello. Am I audible?
Yeah, clear. Please.
Okay. So I'm here on behalf of Sea Convoy. Good afternoon, everyone.
Okay.
So here at Sea Convoy, what we are doing, we are giving as a marine solution for problems like optimization of propellers. So actually, we are not we are into developing of autonomous surface vehicle, as well as we do manufacture boats, model boats for model testing. So for that, what we do is we don't buy thrusters. What we do is we calculate how much power is required for that particular speed, and then we select a motor, and then we optimize a propeller according to it, and then we fit it. So our solution goes in that way. Also, we are into mostly in the carbon fiber hulls. Like now we are targeting our autonomous surface vehicle, which will be of completely carbon fiber hull, which will be lightweight, and of course we can able to put more payload. And also, as discussed already, that we have these sensors quite expensive. We are looking forward for some research organization or institutes where we can collaborate and use those sensors for certain survey and surveillance by using our platform. So our platform will be available. We are looking to collaborate with research institutes for using these payloads until unless we have something very low cost. So this is what we are into, the Sea Convoy. Thank you.
Yeah, thank you for your crisp need and the capability available with the carbon fiber, because that is the one area, another area which will be looked into it because of the density perspective in underwater. So
thank you.
Next we will move on to our VMX connectors, DGM Manoj Abraham, who is available from the VMX. Please share your experience and what you are looking for as an industry partner.
Yeah, good afternoon, everybody. First of all, thank you for inviting us to participate in this program. So we had a lot of new things from different industry partners and NAOT, etc. VMX Connectors Bangalore is a manufacturer of connectors and cable assemblies. We are specialized in marine application connectors. Our connectors are already there in different DRDO programs. We are supplying a lot of connectors to different DRDO programs and their sub-vendors, like the people who manufacture their systems. So we already have connectors which can be catered to your shallow water ROV, which is of 500 meters. So we have connectors which is tested up to 200 bars so far. We have already supplied one cable assembly to NIOT, which has been tested for 150 bars. So in that area, we are already there. And there are some requirements from some DRDO labs for 750 bar connectors. We are in the progress of designing those connectors and getting it qualified. So with that, the completion of that design, we are sure that we will be able to cater to your Matsya 6000 project also. So we already know about NIOT. We have been visited many times and we know about the NIOT activities. We are already working with some of the departments to develop some connectors. So NIOT team has already visited our factory. So we have discussed to develop connectors for shallow water, and then next level of 300 bars, then going up to 6,000 bar pressure. So for any connector requirement for underwater application, VMX is there. We have already proven our connectors for depth up to 2,000 meters. So with this, we offer our willingness to develop any connectors for the ROV applications. Thank you.
Thank you, Manoj Abraham. Because it's actually cables and connectors are one critical requirement for all the underwater vehicles. So all of us will agree on that. So we will make use of that facility. Already the expertise available for underwater purposes. Thanks for your time, for sharing your experience. And next, I will request Senior Vice President from Avar Industries, Amit Kumar Samanta.
Yeah, good afternoon, everybody, and thanks, Dr. Ramesh. Actually,
Yes,
Apar is a cable solution provider. We are manufacturing different varieties of cables, and these cables for underwater application is a typical specialty application. And we have developed, and this cable requires a lot of electrical and mechanical challenges for applications. Same time, we have to meet the electrical parameters and also the electrical parameters. So which we have to balance during manufacturing. And we have developed a lot of these type of cables and supplied to NPOL. And we have recently have supplied one customer ROV, and we have couple of projects which undergoing with NSTL for the
So your audio is breaking, so we will keep note of your details.
So we Apar is there for servicing this type of or development. Hello.
Thank you. Because Apar Industry, we could able to get 2 umbilical cable right now, what we are using for shallow water, and which has been used in the polar temperature also. It was working well in the polar water. That was the one first outcome, Indigenous, and the cost wise, when we are going for the imported one, at the time it is very less, but it is a good cable.
Yes, we have supplied NPL also, a couple of cables.
Yes, sir. Yes, sir. Thank you. Next we will look for Planish Technology. Anthony Jacob Ashish, please. Is available? Okay. Can I request our Kannappan Palaniappan IROV CTO? Can he share about because he has developed an ROV, a smaller ROV with the NPOL?
Good afternoon all. Myself Kannappan Palaniappan. I am the CTO and co-founder of IRO Technologies. We work in the area of underwater platform developments and marine technology. Marine robotics is the area where we mostly specialize on. So we have our systems called IRO Tuna, which is 100-meter rated observation class ROVs. And now we are working in larger size ROVs for up to 300 meters. And we mostly work in the space of marine technologies, particularly for inspections of critical assets. And we are also into the space of development and custom manufacturing of platforms or underwater vehicles, and we have supplied few platforms for NPOL and recently to NSTL also. So that's the area where we work on, and we are also looking to use our platforms for search and rescue applications, and we are also trying to work with defense also in this area. So that's about IRO, our company, and some of the vendors who already are mentioned are also helped us in some of the indigenization of components, particularly Apar cables. We have worked with them for development of tethers, and also we are trying to work with VMX for development of these underwater connectors also. So what areas where we are having challenges, I think mostly team members from L&T has clearly mentioned. So that's the similar areas where we are also sensing, particularly on the sensors, mostly on the acoustic based sensors, and also on the position systems. They are some of the components which we are totally dependent on the foreign vendors for them because of their reliable outputs. But yes, we are also closely trying to work out and see what is the technology that can be brought out from NPL, particularly on these areas which we can utilize of. So that's something we are exploring. But as such, at present, there isn't much options left out for us. And secondly, some of the points which was highlighted by BEL on the business viability and the order volumes of such development. So these are the two areas which, as a young company, which we quite often feel is a challenge. And something on the inquiry is that as we are seeing some of the amazing works which is being done by NIoT, particularly on the deep sea mining, we would like to explore also which are the areas where we can collaborate in the developments. And also I have just spoken with Promosar also on various areas where with NIO and similar CSIR organizations, where such a areas where we can collaborate on the areas of navigation, propulsion, and also on the AML areas of the data processing. That's where we are working on. So that's about the company and the areas where we would like to collaborate with. Okay, thank you. Thank you for the time. Yeah.
Thank you, Pandit. Thank you. Thank you. Thanks for your time. Actually, almost we covered, but whether we missed out to some industry who are already online participation, just I want to make sure. Yeah, just I'm looking for actually Tiwari. He's always available, Shiv Tiwari, and closely watching. I request your presence, sir, actually.
Thank you, Dr. Ramesh. Firstly, thank you for inviting us on this panel and this forum. I'm Commodore Shiv Tiwari. We run a startup ourselves as a veteran initiative, which is Arista Solutions. Principally, we are working in the space of bridging the gap between the stakeholders' requirements and the industry. As a solutions provider, we are presently working with Ministry of Earth Science on a security studies and solutioning project for the Kalpasar Dam project with NCCR. And we are also closely working with various industries. Some of them are represented here. Few thoughts from my side. Firstly, I'd like to share that it came out very apparently and clearly today that between the research organizations, the technology developers, the industry, there is no dearth in this country about talent and the understanding of what we need. And I refer to Dr. Ramdas's opening address where he said we need to work together. And I think this platform of iConnect again is a great initiative to bring everyone together to hear the industry perspective also. Couple of things which I want to highlight is that to start with, our experience tells us that the stakeholders' requirements, the operational requirements of the environment need to be integrated with the technology. So there, in our opinion, there are three foundational pillars towards Atmanirbharta, and that is principle being technology. Second is institutional support, which is coming in a big way. And the third is the operational knowledge. Once all these are combined, we will get truly, independent or self-reliant and Atmanirbhar. And so therefore, one of the key things which I think also brought out by Commodore Srinivas and other people on the panel is that we need to look at mission-based product development. What the industry faces the greatest challenge is that after the development and innovation, how does that capability finally translate? Where are the orders? So that finally a cash flow can happen and sales can happen and capability induction happens. So for that, I think an ecosystem needs to be created where the stakeholders are brought in on board. We are working closely on certain IDEX challenges where a great thing which has happened is that now the IDEX challenge, the MOD is coming out with certain MOQs, minimum order quantities. So that if you do a prototype development, there will be also an order placed on you. So I think that's a great initiative. So mission-based products, if they're defined from these technologies that we are talking of, will end up with capability enhancement in the country. And the last part of this is that beyond the mission-based capability development is also about working together on problem statements which are defined by the industry and then realized collectively. So on a project-based approach. Unfortunately, what happens is that we do not define a definitive project, and I think Commodore Srinivas also said strategic partnerships. And I think that is one of the key aspects of bringing together as a collective community, which is that project towards which we are doing R&D and taking it forward. Whether it is at the larger level of products or even small level of products which the startups are working towards. So I think it's a great start, and we would love to continue to be participating in sharing our perspectives, especially in the defense and aerospace sector with the startup community and institution like NIO and NIOT. Thank you so much.
Thank you very much, Diwali, actually. Because your points are well taken, and maybe the more iConnect even can still forge our partnership well. So finally, yes, we are running short of the partnership well to panel chairman. Dr. Srinivas, already you had spoken about it, and you want to say something because it can be short.
Yeah, just one statement. I just want to conclude by saying that all we have been talking about needs a lot of skill, and the skill needs to be sustained. Both the knowledge from the individual perspective and as an industry to support this requirement. So unless the strategic partnership concept is promulgated or initiated by the ministry, it cannot sustain. Maybe this euphoria will all start something, but for this to be sustained, a policy directive and the concept be pursued by the ministry. So this is what I urge upon the ministry. Vijay Kumar sir, I met you before also. This is what is the crux for us to sustain. Otherwise, we'll start something and it will just die out. That's all from my side. Thank you very much.
Thank you, sir. I thank all the industries who came forward in a different perspective of the requirements for these things, and we had kept note of it. And I submit to the chairman for this panel discussion, Dr. Vijay Kumar, to sum up this panel discussion. Then we can go for the vote of thanks.
There is one sentence I would like to say, Dr. Ramesh.
Yes,
there have been a lot of things about that we have very low volume, but right now it may seems to be low volume given the Indian coast of 7,000 kilometers and resources on the land being depleted. Very soon, a lot of things, near future itself, we will take energy sector or even offshore aquaculture, which requires the similar equipments which are needed for these robotics, would be coming up. So it's not that because of low volume we should, it would take some time, but there is definitely, if we see the future, it is not, it is very bright in marine observations. Thank you.
Yeah, thank you. Thanks.
Thank you, Dr. Ramesh and all the participants from different industry. So listening after all the participants and the industry, I have noted that there is a good amount of expertise is available, whether it is with the L&T, ECIL, who have dealt or dealing with the defense, you can say, the systems, and then other industry also, specifically Bell is there, then Sea Conveyors is there, some connectors. So we have capability for connectors, cables, other connectors. Only if we have to move further, we need to enhance this capability up to say 6,000 meter depth. So some capability is there up to 2,000 meter or less than that, but we need to enhance that thing. And I think there is a need also. But some of the participants has said that about the sensors also. So that is very true. We are not very much in the development of sensors. Whatever we are doing, we are, you can say, purchasing sensors and then assembling that into our own systems. So I think somebody has to take lead in that also. And this is not only specific to our say ocean technology or ocean part, in atmosphere part and all that also. Sensors mostly we are acquiring from foreign. So there is a need for having a look at this thing so that we can also start developing some of these sensors. And as said by my colleague from NIO, there is a in the future we may get more requirement of these systems. So we have to take care of that and start working on that. So I think with this our today's event, many presentation has been made. So both are now the government organizations, institutes who are working in this area, and the private companies who are working in this area, they now well aware of what are the capabilities, what are the needs of different industry, different organizations, and I think they will keep touch with each other to have more interaction and more development, and whenever there's some issue is there, I think they will be able to solve. And also I hope some report or something will be prepared out of this event, so that it can be also passed to the higher authorities to take care. So lastly, I thank all the participants, and also I thank NIOT and NIO for organizing this event and inviting me to chair this panel discussion. Thank you.
Thank you very much, sir. Thanks for your time. And you know that how busy we'll be in the central at Delhi. Thank you very much. And we will keep note of all the points, and then we'll make a document. Before we go for the formal vote of thanks, I would like to thank all the members from the industry and then the organizations who has participated for today's meeting of iConnect. And also I would like to thank actually Pramod Maurya to take forward whenever the gaps were there when I am not available, and my colleague Mr. N. Subramaniam, who coordinated, who can make the possible for connecting all of us today, and then the CSIR support towards this. I hand over for the vote of thanks to Mr. N. Subramaniam. Please.
Yes, sir. Good morning to all. Actually, it is indeed gives me immense pleasure to present summary and vote of thanks for this event. As it has been already summarized, I would like to present the summary in brief. It has been started with the plenary talk of our director on Indian scenario on underwater vehicles. It covers all our vehicles, ended with man submersible and challenges. Then it has been continued by actually Pramod Maurya from NIO regarding, I could say, all autonomous underwater vehicles, as well as and from our actually seniors and Dr. Ramesh and Dr. Vedachalam regarding our unmanned vehicles which is developed here and manned submersible which is being developed at NIOT with all its challenges. Then it has been actually taken over by Dr. Nandi on for autonomous underwater vehicles and indigenous efforts. Then it has been continued with Dr. Srinivas from L&T, especially pointing out all the challenges. Then I'll come to formal vote of thanks, actually. And of course, with panel discussion, we had a wonderful panel discussion headed by actually our chair, Dr. Vijay Kumar from Ministry of Earth Sciences. So, and we thanked him for his immediate acceptance and to have this wonderful actually panel discussions. And to enter into the formal vote of thanks, and we would like to thank Dr. V.M. Tiwari and team nodal of the event and Director NGRA for providing us directions and guidance to connect to the industry using iConnect platform, not only for existing technologies, but also extend to discuss future needs. We sincerely thank our Secretary MOES for this great opportunity. We submit our sincere thanks to our Director Dr. Ramdas, NIOT, and Professor Sunil Kumar Singh, Director CSIR NIO, for extending all support required for this meeting to happen. We take this opportunity to thank Gopal Iyengar MOES for his initiatives. We thank Dr. Hemant Kulkarni, CSIR headquarters, for his guidance for showcasing technologies and to include panel members from all sector of industries, besides especially startups. Actually, we would like to thank Dr. Vijay Kumar and sincerely advise Sir, our Ministry of Earth Sciences, for immediately accepting our invitation as a panel chair and to throw light in the government thrust areas under deep ocean mission. Thank you, sir, who is available here. We thank our coordinators, Dr. Ramesh and Mr. Pramod Maurya, for coordinating activities which drive towards successful event today. A special thanks to Mr. Pramod for his holistic approach. He is always available for the entire events and taking care of everything A to Z arrangements. Thank you, Mr. Pramod. We thank Dr. Ramesh, our moderator, for smooth execution and who has been moderating the event very nicely since morning till now. We would like to thank all our panel members from industries, ECAL, BEL, L&T, Sea Convoy Systems, Planis, IROB, BMX Connectors, APAR, and other industries. We would like to thank Ms. Palak and team from NFDC, especially for the continuous support extended to provide web page, posters, and panel meeting support, including these arrangements. Last but not the least, thanks to all the participants, audience who participated in the event by registration or through direct link by YouTube. Thank you all.
sir.
Thank you so much.
Thank you everybody. So we will all of this meeting now.
Maybe we can take a screenshot.
Yeah, please. So maybe all the people may turn on their cameras so that they can take a photograph.
Just one more. Thank you very much. Thank you.
Thank you. Thank you. Thanks for all.
Thank you.
Thank you. Thank you. Bye.
Thank you very much.
Thank you. Have a very good day.
Thank you. Thanks a lot.
Nice to see you, Srinivas sir, after a long time.
Hi, Santosh.